Okay, sir.
Hello. Please let me know if I'm audible to you, everyone. If someone is there, please confirm whether I'm audible or not. Hi, Ambrose. Good morning. Thank you. Thank you for confirming. Yeah, thank you, Deepak. So we'll start with the GATE CSC operating system course. So it will be quite rapid mode course. So I'll start with the basic briefing of the concept and then we'll jump to the previous year questions. Okay. So I'll cover these particular topics. Okay. The important topics that will be important with the perspective of the GATE exam. Okay. So those topics having the questions majority in marks obtaining part, I'll cover that particular section only. Okay, so we'll start with the uh, basic concept. What is operating system that you know? Okay, so we'll start with the basics of the operating system. Uh, the definition of the operating system, types of the operating system, and the major objective of the operating system, and then we'll jump to the process, then to the CPU scheduling, then process life cycle, and the uh, process synchronization. We know that multiple processes are there in the system that are trying to access the resources, and in that particular case, to have the consistent output, or we can say the unredundant output, we need to have the process synchronization. Deadlock, if some particular process is already having some resources and waiting for another resource which is obtained by any other process which is not releasing that particular resource, in that particular case a process may be hanged or process may be halt for the long duration, and that particular case we can say it is the deadlock scenario. Okay, so we'll look at the various conditions that may cause the deadlock scenario, and then we may have the corresponding outcomes that how we can resolve such kind of situations. Okay, then we'll look at the memory management. From memory management perspective, we have already considered the cache memory management in computer organization architecture, so I'll leave that particular part there. Okay, and then we'll consider the virtual memory, that how virtual memory is mapped into the actual physical memory, and then we'll look at the demand paging and the various page replacement algorithms. Okay, and then we'll discuss about the main memory. Okay, how to secure that particular main memory via hardware way or via the software way, or what are the different concept of fragmentation, segmentation, paging, and all that. Okay, and based on these concepts, certain previous year questions. All right, so we'll start with the operating system. That how do we define an operating system? So you can give me a message or ping to text in between if you have any doubt, any query related to the running concept. Okay, so just give me a simple chat message over here in the chat box. All right, so we'll start with this operating system. So we normally consider operating system as a interface between the hardware and software. Okay, so what are the softwares? It should be application software, it could be some drivers that are eventually considered as the system softwares. Okay, so operating system is nothing but a mediocre between the user and the hardware. Okay, so user can interact with the application softwares or the certain drivers, certain hardwares. Okay, and it is trying to access a particular hardware, and that hardware may be the CPU, the register, or the IO devices, the memory. These are the hardwares that are treated as the precious resources of this particular system. Okay, so if you recall your von Neumann architecture, that there you can see that CPU has certain IO devices, certain uh, input and output devices, and that has some external memory. So the user can interact with the input, okay, or can interact with the output device, and so it certainly requires some hardware devices. It is trying to read certain file, or it is trying to modify certain file, so it is trying to access the memory, okay. uh, or it is possible that it is computing something, and that computed result is going to be displayed on the monitor. So again, in that particular case, it is trying to access the registers, CPU registers, okay. So the objective of the operating system is to synchronize the entire process, okay, to manage the entire process, to interface between the user and hardware, to have a smooth transition between each and every request, okay. And apart from this, there are various other applications, like various other, you can say, uh, the features that should be provided by the operating system, and that has a very, you can say, the large number of definitions that it could provide. The security, it could provide the like data integrity, it should provide the data consistency, okay, it should manage the logs, it should protect the information, okay. Resource allocation, like how if multiple users or multiple processes are trying to access the single CPU, in that particular case, how it should be allocated to each and every one, in which particular duration. The management of the memory, management of the IO devices, management of the file systems, and all that, okay. Error detection and recovery, in that particular case, if some hardware or some process failed, in that particular case, what precautions or what measures has to be taken by the operating system, so that it can detect and recover the corresponding error. It also provides a way to communicate between the processes, okay. So various processes can communicate, uh, so the communication is required, so that they can transfer the information to each other, so that they can easily know whether the particular resource is free for their use or not, okay, or they can enter into the critical section or not. So such kind of communication must be provided by the uh, operating system. Okay, so like a program execution, if there are, say we are executing a particular high level language program, so the compilers and different interpreters, or you can say the different types of translator, can actually convert that high level language into the object code, and that should be executed, and the output, corresponding output should be managed by the operating system. So these are the various tasks that has to be done by the operating system, okay. So even in that particular case, it is required that whenever we are trying to execute a particular process, uh, that could be executed in two ways, okay. That could be executed in the user mode, or it could be executed into the kernel mode, okay. So that is another important aspect, that in kernel mode, the kernel mode is the privileged mode, in which the uh, basically the operating system tries to manage that particular part. So in that particular case, hardware access is granted to the particular process, okay. Like in user mode, any process can get access, but any process can get executed in that particular mode, but it doesn't have any hardware access, okay. But in kernel mode, the process can get executed, and that could actually have the access of any particular hardware, okay. So there is another concept, that whenever we switch from the user mode to kernel mode, and that particular concept is known as context switching, okay. And in that particular case, there will be a system call, that are the interfaces to the services provided by the operating system, okay. So that is important task, that various types of systems calls are there, that has to be managed. Like there is a process control system call, there is file manipulation system call, device management system call, information management, or the communication. So these are the various types of system calls that has to be managed by the operating system. All right. So we'll look at the various parts here. So operating system's goal is to execute a particular program and make solving user problem easier. Okay, so this user programs can be executed in either system mode, user mode, or in kernel mode, allocating the particular. required of hardware. Okay, make the computer system convenient to use. So how it is convenient to use? If any particular process is trying to access any particular resource and if it is not required, that is not a convenient way. Okay, so this is the task of operating system, that if n number of processes are running into the particular system, it can manage the hardware so that each and every process can easily get the access of that particular resource. Use of the computer hardware in an efficient manner, that is obviously we have discussed. Okay, so just look at this particular diagram. Here in this particular diagram, you can see that n number of users are there. They are interacting with the computer. Okay, and they are interacting with basically through certain applications. Okay, so here you can see that certain applications are there, that is the compiler, assembler, text editor, database system or music system and all that. Okay, so n number of devices can be there, n number of applications can be there, and users are interacting with those applications. Okay, so these are the application programs, and sometimes if they are using certain dedicated hardware, in that particular case they are using basically the system softwares or the drivers. Okay, so this particular layer is the mediator level between the operating system and the application programs. Okay, between the users. So application program lies between the user and the operating system. Okay, so the operating system has the basic role how to manage these applications to interact with the computer hardware. Okay, and that hardware basically deals with the CPU registers. Okay, and you can say the IO devices. All right, and the memory obviously. Okay, so this is the task of operating system, how to manage all these things. Okay, even it is possible that one particular let's say it has certain process, the user have one has certain number of process, and that process trying to interact with the user third process, that it is trying to communicate with this. So that communication is done via the operating system itself. So uh, it must provide certain mechanism to have the communication between running process. Okay, so so apart from this, there are complete chapter on this, the basic introduction, where you can have the complete introduction related to all that particular phases. So what about the process, what about the inter-process communication, what about the threads, what about the process synchronization, various types of operating system. So if you look at the various types of operating systems are basically defined as batch programmed operating systems, that is normally called as batch OS. Okay, time sharing operating system, where the processes are based on means if real time systems, we talk about the real time systems, they are based on the time quantum. Okay, the distributed operating system, where the resources are distributed in various platforms. Network operating system, that used in networking concept. Real time operating system, multi-programming, multitasking, multi-threading, multi-processing. Okay, so these are the various tasks, various types of the operating system. So in this particular concept, if we look at this particular session, we are trying to cover the multiprocessing or multi-programming part, where multiple processes are running into a particular system with uh, possibility that a system may have only one CPU or system may have multiple cores of the CPU. Okay, so if you look at uh, the old era, when one CPU is there and you are trying to execute multiple tasks. Okay, then in that particular case, it is not feasible for the CPU to run multiple processes at the same time, because CPU can execute only one process at the time, and rest other has to wait. Okay, but now look at the current scenario, that one CPU may have multiple cores, so you can have the quad core, octa core, dual core, and so on. Okay, so in that particular case, multiple core of the same CPU, so parallel systems are there in your uh, uh, single CPU bed. In that particular case, the multiple cores of the CPU are there with its own dedicated registers, but with shared memory. Okay, and the shared common bus. Okay, in that particular case, each and every CPU has to interact with the single main memory. All right, single IO devices that you have. Okay, so each to to allocate these resources to every demand of the CPU. In that particular case, operating system has to play a critical role, okay, so that it can manage the deadlock scenario. All right. So what about the process? Like whenever we run a particular program, see, whenever if we look at the definition of the layman process, we can say that a running process or a running program is called as uh, process. Okay, so that is not the complete definition. That like if we run a particular program, if we have high level programming language, we can execute that, we can have the binary code. Now we can't say that that particular binary code is the process, okay, because that is non executable part, that is loaded somewhere in the memory, but that is not actually comes into the execution. Whenever you select a particular block to get executed, in that particular case, when CPU is allocated to that particular instruction, that will be called that process which is under execution. Okay, so a small chunk of entire program is under execution, so that is called running program. Okay, so a program in execution, so that is called the process. Okay, so it is possible that one particular program may have n number of processes. Okay, and further these processes are further categorized, further classified into n number of threads. Okay, so one particular program may have n number of threads, one particular process may have n number of threads. Okay, and these threads can run concurrently. So the process can run concurrently and the threads can run concurrently. So if concurrently running process demands the particular resource, and if the resources are independent of use, in that particular case, there is no problem that we can allocate each and every process the required resources, and they can run parallelly. Okay, but if they are dependent, what if they are dependent? That if any particular process is requiring a particular resource and that resource is already allocated to someone, okay, so in that particular case, the running process has to wait, so that the resource, once resource is available, it will get allocated to this demanding process, and then it can get executed. Okay, so this is important aspect that we have to uh, take care in this particular case. Okay, so the processes are nothing but the program that is in execution, which forms the basis of all the computation. Okay, so we'll look at this particular concept in deeply. So the various features of the process are including the scheduling, creation and termination, and the communication between the process. Okay, so when they are created, so there are certain life cycle of a particular process, starting from the creation to the termination. Okay, so that particular section is defined by this creation and termination, and then there's scheduling, that n number processes are trying to access the resources, then in which particular order they are supposed to be allocated and executed, that is called scheduling. And the communication, if they are trying to change the information between each and every process. Okay, so we should explore the inter-process communication during the shared memory and the message passing. Okay, to describe the communication in a client server system, like if you look at the client server architecture, in that particular case, the communication is only possible with the hand setting, that one has to request, another has to response. Okay, so that is another important term over here. If you look at the process in memory now, if you are going to look at the process in memory, then you have to consider the memory layout first. Okay, so the entire memory, the main memory, if I am talking about the memory, it is nothing but the primary memory. Okay, if I am talking about the disk, then it is the secondary memory. Okay, large storage, the persistent storage. If it is the term memory throughout the subject, in that particular case, we are talking about the primary memory. All right, so if you look at the particular process in memory, that means one, your process is faced from the external device to the main memory. In that particular case, it can be loaded into different section. Okay, so look at the classification of the memory, that memory has a multiple segments. Like if you recall the 8086, in that particular case, there are four segments: the code segment, data segment, extra segment, and uh, the stack segment. Okay, so they are having the dedicated task that the programs can be loaded into the code segment only, stack related instructions can be loaded into the stack segment only. Okay, entire data, whether it is a normal ordinary data, it is an array, all that data elements are required to be stored in data segment. Extra segment is used for multiple tasks, like if someone is having the less memory space, then that particular segment can be extended to utilize this extra segment. Okay, but if we look at the ordinary our normal memory structure, that memory layout, in that particular case memory layout is divided into basically four section. This is not the correct representation. If you look at that part, so it is basically classified as, so right. All right, so this is called the stack memory. Okay, and this is the heap memory, and basically it is represented as the dotted line. Okay, so dotted line represents that this is the minimum available limit, minimum available size, and it can expand. Okay, and this heap is also can expand. So actually there is no proper division between the stack and the heap memory section in that particular case. If heap size is further required by the storage of any particular data item here, in this particular case it can grow or it can shrink depending upon the dynamic requirement. A stack is also can grow and can shrink, but there is a logical partitioning that it cannot go beyond this particular size. Okay, so it has certain max and mean criteria as well. Okay, then there is a data. That particular data is nothing but the static or the global data. Okay, and this is nothing but the OS kernel section where the kernel can be loaded. So you must have the concept of the bootstrapping, that whenever you, like, operating system acquires around 3 to 4 GB in the memory. So it is not possible to load entire operating system into the main memory, because main memory is volatile in nature. So whenever you turn off your system, that is going to clear the entire data that is available in the RAM. So we cannot load that particular entire program into that operating system into the main memory. So what we can do, we are basically storing the operating system into the external memory, that is into the secondary device, and its kernel, which is actually having the information of the location where operating system is loaded into the program, and what are the important files that has to be loaded into the main memory for execution of the or for booting up the entire operating system. So that particular kernel and important and necessary files are loaded into the ROM. Okay, and that ROM is again non-volatile memory, so that is primary memory. So whenever we start our system, the BIOS or that ROM kernels are loaded into the main memory, and that kernel actually plays the important role to fetch all the important files that are required to be booting up the entire process of the operating system. Okay, so that bootstrapping concept must be known to you, that basically plays by the important role plays by the kernel. Okay, so this is the this particular section is the reserved space for the operating system. Then we have some static and global data elements. Okay, so all the variables which is defined as static or global, that has to be allocated into this particular data section. Heap, that is the dynamic allocation of the memory, that at runtime required elements has to be stored in this particular section, and the stack related. So this you can say the general purpose location where all the devices can all the process can actually fight the for the execution. Okay, so if you look at the particular process, that when there is a process that is a program which is under execution, then it has a definite state. Okay, when any particular process has created, that is called a new process. Okay, so that is the new state of the particular process. The process is being created in that particular phase. uh, if it is running, that means it is already allocated the CPU, and that process is under execution. Okay, so that is a running state. Waiting state, that means when a process is running and it requires certain IO operation, or it is trying to access the memory. In that particular case, it has to go back to the waiting state, so that during that particular time your CPU can start executing the another process. Okay, because this is the primary objective of multi-programming system, that our CPU must be busy all the time. Okay, so if I keep our CPU at idle state during the waiting state of any particular process, that will be the poor utilization of the resources. Okay, so our maximum approach is to keep busy CPU. Okay, so in that particular case, if any particular process requires the IO or the memory access, in that particular case, CPU must be kept out of that particular process, allocated to another process. And in that particular case, your the deallocated process has to wait for the IO. Okay, once it has completed its IO, or it has done the IO operation, it may demand for the CPU. Okay, in that particular case, it has to switch back to the ready state. So ready state is the particular state when process is waiting for the allocation of the CPU. Okay, that means it is created or it is from the waiting state. In both cases, it will once it is created, it has to be loaded into the ready queue, so that it can further get allocated to the CPU. Or when it is having done the IO operation, it has to go back to the ready state and to perform the CPU if required. Okay, and terminated when process has completed its execution, then it has to be terminated, or it is sometimes called as dead state. So just look at this particular diagram. So this is the particular state where the process has created. Okay, so every process created is kept at this particular state, so it can be treated as nothing but the job pool. Okay, so n number of jobs have been created and they are kept at this particular level. Okay, now some process which is required to get executed, they are admitted to the ready state. Okay, so this is the queue. Okay, so this is the queue data structure where all the process has to be kept over here. Okay, those who are fighting for the CPU. Okay, those who are fighting for the execution. Okay, so there comes a task of scheduler and dispatcher. Okay, so this is the short term scheduler, which has a task of selecting a particular process from the ready queue. Okay, now it could depend upon the specific algorithm, like it is first come first serve, it is shortest job first, shortest remaining time first, round robin, or the priority scheduling. Depending upon that, it has to select a particular process from the ready queue. Now once a particular process is selected, dispatcher has the task to allocate that particular process to the CPU, dispatch that particular process to the CPU. Okay, so this is the task of scheduler and dispatcher, to select a particular process and allocate it to the CPU. Once the process has been allocated to the CPU, that will jump into the running state. Okay, once the process is in running state, there is possibility that it can get executed completely, because that doesn't require any IO operation, or it could have a certain IO operation. Okay, so two possibilities are there. Another possibility is that whether it is terminating, it doesn't require any IO, or it is requiring IO. Third situation is that in that particular situation, any other high priority process is appeared there for the execution. In that particular case, the running process has to be shifted back to the ready queue. Okay, and the high priority task has to be executed first. Okay, so there are possibility that if the running process is interrupted by any high priority task, it has to go back to the ready queue. Or it is possible that the running process has completed its execution, that will terminate. Okay, or it is trying to having the certain IO operation, so in that particular case it has to jump into the waiting state. Okay, and after the completion of IO, it has to jump back to the ready state. Okay, so the obvious task of the CPU scheduler is like when there is a requirement of scheduling. The requirement of scheduling is here when the process is in ready state. Okay, n number of processes are there waiting for the CPU. In that particular case, it has to be selected by the scheduler dispatcher uh, at this particular moment when the process is terminated. Once our process is terminated, another process has to be executed because we need to keep CPU busy. Okay, in that particular case, the selection of any particular process is required in this particular scenario. Okay, or when it is like process is waiting. Okay, in that particular scenario again, because that running state is free. Okay, the running process is shifted back to the waiting state for IO operation. In that particular case, CPU is idle, so CPU has to select any other process for execution. But in this particular case, CPU scheduling is not required. When any other process is interrupted, then there is forcible allocation of any particular process for the execution. So CPU is not free at that particular moment. Okay, so there is three scenario in which we have to select a particular process for the execution. Okay, so the running state, ready state, terminated state, or whatever is the current state uh, of any particular process, what is the process number, what is the program counter value, what are the registers allocated by utilized by that particular running process, what is the memory limit corresponding to that particular process, number of opens files that are basically allocated to any particular running process, that has to be maintained by the operating system, and that is maintained by program control block. Okay, or you can say the process control block. Okay, so the process control block in operating system is managed, that is actually maintaining the is detailed status of any particular process. So what is the state of the particular process, whether it is running state, ready state. So depending upon the life cycle of that particular process, it has to be maintained over here in the process state. Okay, so what is the process number, that if n number of processes are created, then certainly we have to number each and every process. So that process number has to be marked over here. Program counter. So program counter is the another important special function register that basically maintains the address of next instruction to be executed. So that particular information has to be maintained, because each and every time whenever another process is executing, or one particular process is calling another process, in that particular case remainder section has to be executed further. Okay, to maintain that, we need to have the updated information in the program counter. Okay, so we'll use this particular program counter along with the stack. Okay, to maintain the recursive call or the function call or the process call or the thread call. Okay, all that information has to be maintained, or if there is any kind of interrupt, if there is any kind of jump. Okay, so all that uh, information has to be maintained through the program counter and stack uses. Okay, CPU register, that if certain operation has been performed by the particular process, the registers are supposed to be allocated in that particular case. Which registers are allocated? So this allocation and deallocation of the registers are basically managed by the graph coloring concept. Okay, so if n number of processes are there in and m number of registers are there, then which particular register is allocated to which particular process has to be managed by a specific color of the uh, that particular registers. Okay, so that is one wonderful application of the graph coloring in register management. Okay, register allocation and deallocation case. Okay, memory limit, that any particular process cannot go beyond the certain limit of the memory, so it has to utilize a memory layout. Okay, in that particular case, what is the specific allocated memory, each and every process has to start from a particular base address and has to terminate in a specific range. Okay, so that memory limit has to be defined corresponding to this particular process. List of open files, that specifies that whenever any particular process is executing on any particular file, which particular file is open in which particular mode has to be maintained in this particular section. So these are the corresponding information that has to be managed, and many other information has to be marked over here. So there is no such question from this particular section, so I'll just skip this section. So this is the CPU switch from one particular process to another process. Let's say one particular process is executed, and in that execution, okay, so p0 is under execution, and the operating system is managing the basically PCB of that particular process. P0, and there is one process P1 which is uh, interrupting this running process. So whenever it is interrupting, so here you can say that this is the interruption stage. At this particular stage, the CPU has to be allocated to this particular P1. Okay, this particular process P1. So what has to do that this is the remaining section of this particular program. Okay, this is the remaining section of this particular program, or you can say the process P0 that has to be maintained. Okay, in that particular case, our that state, whatever the state of this particular process control block PCB0 has to be maintained. So in that particular case, the program counter value, the registers value, the files value, all that information has to be saved. Okay, and once this P1 has executed, and in that particular case, again we have to reload the PCB0 for further execution. Okay, so this is the maintenance of the switching between the one process to another process, whether it is a high priority or it is selected by a scheduler. Okay, so that is the basic concept, that is the base that provides you the basic concept, like if n number of processes are running into the system, in that particular case it is mandatory to synchronize the running of that particular process. So we need to have the CPU scheduling concept between these running process. Okay, so CPU scheduling is nothing but the process of allocation and deallocation of the CPU to any particular process in order to maximally utilize the throughput, the running time, the response time, and all that. Okay, so we'll look at the certain parameter of the CPU scheduling. Okay, so before that, we must know that CPU or any particular process has to follow a cycle that is called the CPU burst and IO burst. Okay, so here you can see that this is the CPU burst, then IO burst, and every time the cycle starts with the CPU burst and terminates on the CPU burst itself. Okay, so it must terminate on CPU burst also. Okay, so whenever a process enters into the execution, it first reads the CPU burst, start executing, and if now in at that particular moment it requires any IO operation, that it look for the IO burst. Okay, so it has to wait for the IO, and in that particular meantime, in that particular IO burst time, my CPU is idle. Okay, so what we have to do, we can allocate another process at that particular time that it can utilize the CPU burst at this particular moment when the process P0 is waiting for the IO. Okay, the process P1 can start executing this. Okay, so that particular concept we have already taken into consideration in CPU pipelining concept, that instructions are running parallelly. Okay, in some shifted concept. Okay, so again that is utilizing that fetch, decode, execute, and all. So the decode process, like in this particular duration, one instruction is phased till decoding. CPU is free. Okay, in that particular case, CPU can execute any other process. Okay, so this particular CPU cycle has to this you can say the time has to be divided into the CPU burst and IO burst that should be utilized by the n number of processes running into the system. Okay, look at the scheduler. That short-term scheduler has to select the particular process that has to be allocated CPU. So each and every process which is kept in ready queue first has to be selected by the short-term scheduler, and that depends upon the various ways. Like we'll look at the concepts. Okay, what are the various ways through which we can actually select a particular process, and then once it is selected, okay, that has to be allocated for the CPU. Okay, once it is allocated to the CPU, there is two possibility that the CPU is running the particular process. Now it could come under two categorization, whether it is non-preemptive or preemptive. Okay, so look at the decision on which the CPU scheduling is done. First one is the switches when a particular process is running on a CPU, it switches from the running to waiting state, it switches from the running to ready state, it switches from the waiting to ready state, or it is terminated. Okay, so these four possibilities that we have already discussed in the process life cycle, that whether your process is shifting from running to waiting state, shifting from running to ready state, shifting from waiting to ready state, or it is terminated. Okay, so these are the four criteria which we have to consider for the CPU scheduling. Okay, in this particular case only we may have the choice of selection of any particular process. So the scheduling criteria 1 and 4, if you look at the criteria 1 and criteria 4, that the switches from the running to waiting state or it is terminated. In that particular case, we do not have any fighting process for the execution. Okay, in that particular case, we need to select a particular process from the ready queue. Okay, so it is called as non-preemptive. Okay, we do not have applied any force to preempt the allocated CPU. Okay, so it is by choice. Okay, it is by choice that a particular process has switched shifted to the waiting state. Now CPU is idle in this particular scenario, or it is terminated. There is no further choice. Okay, it is terminated. Now CPU is completely idle. So this is the ideal situation which is generated by the process. It is not by deallocation of the process. But if you look at the 2 and 3 point, where it is switches from the running to ready state, it is switches from running to ready state. That means any other forcibly running process is doing this, so that is called interrupt. Okay, so high priority process has occurred for the execution. In that particular case, uh, forcible concept is applied. That means it is preempting the running process and deallocated to the high priority process. Okay, switches from waiting to ready state. Now if some process is running shifted from waiting to ready state, it is not necessary that ready state is free. Okay, in that particular case, there are k number of processes already there in ready state. One more process is included in ready state from the waiting state. In that particular case, the scheduler has to pick any one from that particular k plus one total process into the ready state. Okay, in that particular case, again there is a choice of the scheduler based on the certain algorithm. It has to pick one. Okay, so these are the two situations which is causing the primitive situation, and these two are the non-primitive situations. 1 and 4 are the non-primitive situation, and the rest two are the primitive situations. Okay, now there comes, once any particular process has been selected, it is the task of the dispatcher to select a particular allocate this particular selected process to the CPU. Okay, and once that particular process has allocated the CPU, it will start executing. That will simply jump into the running state. Okay, so we need to have the we need to maintain the dispatch latency. That is the time it takes for the dispatcher to stop one particular process and another process. That should be the minimum. Okay, the dispatch latency should be minimum, so that my CPU can frequently execute the process. Okay, no other process has to wait for the long duration. So these are the scheduling criteria, that CPU utilization, that how maximum you are utilizing the CPU, or you can say the CPU is not free at all. But like in ideal situation, we try to keep busy our CPU 100%. But in realistic situation is that we can at most utilize 60% of the allocation of CPU. Okay, so that is the harsh real scenario, that we are utilizing our CPU maximum up to 60%. Throughput, that is saying that the number of processes that completes their execution per unit time. So if n number of processes, if all the processes executed in per unit time quanta, then the throughput is very high. Okay, so we have to high the throughput. Turnaround time, the amount of time to execute a particular process, that is called the turnaround time. Now it is possible that whenever a particular process is under execution, any high priority process is interrupted, that, and in that particular case, this new this deallocated process is never allocated the CPU again. Okay, in that particular case, turnaround time is to be very high. So we have to minimize the turnaround time so that we can have the high efficiency of the CPU. Waiting time. Now again, this is also important term, that the waiting time, that amount of time the process has to be waiting, has to be in waiting for ready queue. Okay, has to be kept in ready queue for the CPU allocation. So this waiting time is supposed to be minimum for high efficiency. response time, that is called the overall time, that time takes from when a particular request was submitted until the first response was produced. Okay, so that is the response time, that like in this particular case, that particular case is available for the time sharing system. When a particular process is waiting for the particular CPU, in that particular case, what is the first response time to the of the CPU or the dispatcher to this particular process. Okay, so we'll look this particular parameters or the criterias, uh, so that we can have the maximum CPU utilization, ideally up to 100% VG, maximum throughput, that maximum number of process per unit time must be allocated, minimum turnaround, that I told you, that minimum turnaround, that in that particular case my process has to be executed in no time. Okay, so how long it take to execute a particular process, so including the wait and memory and ready queue and all that. Okay, so these particular times should be almost null. Okay, so that we can run our process. So the minimum turnaround time should be there, minimum waiting time, that is the total time in ready queue. Okay, so some process has not to be kept in ready queue. If any particular process for infinitely waiting for that, this will be called as deadlock scenario. Okay, so minimum response time, that the time it takes to respond, that should be again minimum. Okay, so only maximum CPU utilization and maximum throughput is demanded. Otherwise, each and every term, every criteria must be minimum. Okay. So we'll start with the scheduling algorithms, that we have variety of scheduling algorithms, that is first come first serve, shortest job first, shortest remaining time first, round robin scheduling, priority scheduling, and the multi-process scheduling. Okay, so we'll consider the most frequently asked question wise. Okay, so the first come first serve is one of the simplest one. Okay, and for this implementation we just need to maintain the queue only. Okay, we need to maintain an ordinary queue. Okay, so here you can see that we have a number of process. Okay, so all these processes having the CPU burst time. Okay, so this burst time is basically representing the CPU burst time. So the P1 will take 24 CPU cycle to get executed, P2 will take 3 CPU cycle to get executed, and P3 will take 3 CPU cycle to get executed. Okay, so if we allocate the first come first serve, like if we consider that P1, P2, P3, this is the specific order of the arrival of this particular process. So in that particular case, you can see that we'll start with the zero time quanta, and we'll take 24 CPU bursts to execute this particular process P1, and then from 24 to 3, that is called 24 plus 3, that is 27 for P2, and then 27 plus 3 for P3 is the 30. Okay, so this is the allocation of the process for execution. Okay, so in this particular case, CPU is busy executing 0 to 24 time for P1, then 24 to 27. Now you can see that my CPU is not in idle situation at any particular moment. Okay, it is consistently executing each and every process one by one. Okay, and if you look at the waiting time corresponding to the process P1 just arrived and allocated the CPU, so it has no waiting time, so it is 0. Now look at the process 2, which has the burst time 3, but it is allocated at 24 unit of time. In that particular case, it has the waiting time 24, and similarly for P3 it has waiting time 27. So we need to compute the average waiting time for all the process. In that particular case, average time is the waiting time of each and every process divided by the number of process. So it is 0 plus 24 plus 27 divided by 3, that is 3 number of processes are there. So it is 17 unit time for each and every process to wait. Okay, so this is the per process waiting time, average waiting time per process. So it is 17 unit time per process has to wait. Okay, now what we can do, let's say I'm just going to switch the scenario. Let's say another condition, that process arrival of the process are, let's say P2, P3, and then P1. Let's say this is the arrival of the process. If I look at this particular scenario, then what we have to do, we have to allocate the process P2 first at 0 timestamp, and it will take only 3 time quanta to get allocated, to get executed. Then we'll allocate another process, that is P3, and 3 plus 3, that is going to be 6. So it will get allocated executed in this particular time quanta, and then p1 is allocated, and it will take 24 times, so it is terminated at 30. So same time is used for execution of entire process. Okay, now look at the waiting time. So waiting time for p2 is going to be 0. So this is waiting time for p2 is going to be 0. Waiting time for p1, sorry, p3 is going to be 3. Now waiting time for p1 is going to be 6. Okay, so if we look at the average waiting time, if you compute the average waiting time here, it is going to be 0 plus 3 plus 6 by 3. So it is nothing but 9 by 3, and that is 3, which is comparatively very much lesser than the 17 unit time. Okay, so what we can do, we can alter this particular occurrence if we have the mechanism to alter the arrival, so that we can have the minimum waiting time. Okay, so the first come first serve may have this particular scenario, and that is specifically called a particular problem here. Okay, so that problem has to be resolved by the shortest job first. So that is the concept we have taken over here, that the CPU burst time which has the lesser for any particular process has to be picked first. That is called the shortest job first. Okay, so we have to select a particular process which has a shortest job that has to be executed first. Okay, so that is the non-preemptive process. Okay, that is non-preemptive process, that whenever we have allocated a particular CPU to any process with the least CPU burst time, will not get preempted. Okay, no other process can uh, cause any kind of interrupt to that particular running process. Okay, so once CPU is allocated, the process will get executed. uh, okay, until the date situation. So this is the non-preemptive situation. Now another improvisation in this is that we can convert this scheduling algorithm, shortest job first scheduling algorithm, into preemptive one. And once we permit the preemption to any allocated process, that is called as shortest remaining time first. Okay, so it is possible that it has executed for a certain moment of time. Okay, and then we have preempted that, and once it is preempted, it has only the remaining time for the execution. So our algorithm says that we only select a particular process which has the least remaining time. Okay, so that will utilize the uh, execution of any particular process. Okay, so we'll look at the quick example of these two, and then we'll jump to the previous year questions. Okay, now just look at the shortest job first. So here we have the process p1, p2, p3, and p4. It has a burst time 6, 8, 7, and 3. So if you look at the particular burst time, then we can see that p4 has the least burst time. Okay, so we can rearrange them. We can rearrange this particular process into ascending order of the burst time. So we can see that p4 must be the first process. Then we look at the process p1, which has the next minimum CPU burst time. Then we have P3, and then we have P2. Okay, so this should be the specific order. This should be the specific order of the execution of the particular process. So here you can see that P4 is executed first from 0 to 3 unit of time, and then so this is utilizing the 3 CPU burst over here. Then P1 is allocated because P1 has the least CPU burst time in this particular case. So P1 get executed for the 9, then P3, and then P2, whatever we have decided over here. Okay, now we have to calculate the average waiting time. So P1 average waiting time is 3 over here. Okay, so P1 has to wait for 3 unit of time. So this is the waiting time for P1. Then this is waiting time for P2. So if you look at the P2, which is waiting for 16 unit of time, then P3 has to wait for 9 unit of time. Okay, and then P4, which is waiting for 0 moment. Okay, so we'll just get the sum of all these divided by the total number of process. So here you can see that the number of process has increased. Okay, but it has comparatively better response, or comparatively better average time than the first come first serve. Okay, so if you solve this particular problem using first come first serve, you can compare this particular process. So if we solve this particular process P1, P2, P3 appearance in that particular order, then in there you can see that the waiting time can vary depending upon this. Okay, so based on waiting time only, we cannot select the particular process. There must be certain criteria. So all that criteria, that response time, turnaround time, and all that throughput, that has to be taken care. Okay, so just we'll look at another example here. The shortest remaining time first. Okay, so the students, those who are in online, they can actually give me a just message over here, that if you have any doubt at any particular moment, you can just give me a message over here. Okay, if you have any doubt at any particular moment, you just give me a message in this. All right. Look at the shortest remaining time first. So shortest remaining time first says that it has certain arrival time and the burst time. So the process has dedicated with the certain arrival time and the burst time. Now at arrival time, let's say process P1 appears for the zeroth moment. So at zero time, process P1 enters into the execution. So it will get executed for the complete cycle. Okay, we cannot deallocate the CPU in between of the CPU burst. Okay, that half cycle is completed, now CPU can be deallocated. No, the CPU will only get allocated after the completion of one particular cycle. Okay, so P1 at least get executed for one clock cycle, one CPU cycle. Okay, so one CPU cycle is executed, and then at that particular moment, the burst time for the process one will be 7 only. Okay, now at that particular moment, at moment one, there is another process appeared, that is called P2. Okay, so P2 appears at this particular moment, and there is P1 already under execution. So what we have to do, we have to look at the remaining time of this particular process. So remaining time of the process P1 is 7, while the remaining time of the process 2 is the complete 4. Okay, and which one is the minimum? So in this particular case, process 2 has the minimum remaining time. So process 2 gets the CPU and it will start the execution. Okay, so it has started the execution at time 2. Now we have to look at time 2. So at time 2, it is executed for 1 second, so its remaining time is going to be updated as 3. Now at time 2, another process appeared, that is called P3. Okay, now look at process P3. Process P3 has the CPU burst of 9. Now we have to compare these three CPU burst time. So the least one is 3 over here for process 2. So process 2 started that continues the execution. Okay, so now at another CPU cycle, that is at cycle 3, it has to check for the further possibility that which one has the minimum. Okay, so at that particular moment, one cycle has been utilized by this, so the remaining time for the P2 is 2 now. Okay, and at that particular moment, at 3 time stamp, the new process appeared, that is having the CPU burst time 5. Now what we have to do, we have to compare 7, 2, 9 and 5, and 2 is the minimum remaining time in that particular case. So P2 has the obvious winner situation, so P2 will get continue execution. At P4, it will again check for any other process to appear. There is no further process and it has executed now, so it has the remaining time 1 here again. So process 2 will get executed completely. Okay, once process 2 had executed completely, now we have to check whether which one has to be selected. Now we have to look at the remaining time first. So 5 is the least remaining time for process 4. So process 4 is selected, and once it is started the execution, every time its remaining time has to be reduced by one. Okay, so we have to compare if it is the minimum among these existing two, it will be continuously decreasing, so it will again remain the least in that particular category. So P4 will execute completely. Now there is only two process, 7 and 9. Okay, so 7 is the least remaining time. In that particular case, P1 is selected. that will execute from 10 to 17, and then after the last process P3 will get selected for execution. Okay, so that is the shortest remaining time. So that says that each and every time quanta you have to check if there is any new process or if there is existing process, and which one is having the least remaining time. Okay, according to that you have to select. Now we have to calculate the average waiting time. So calculation of average waiting time for this is a little tricky. In that particular case, you have to actually look at the computation of the time based on this mechanism, that when it has entered into the process. Okay, so this is the formula. You can see that total waiting time minus the number of millisecond it is processed, that means it is already executed, and the arrival time of that particular process. Okay, so by this we can calculate the waiting time. So here you can look at the process P1. So process P1's last waiting time is 10. Okay, process P1 enters into 0th time stamp, but it again has to enter at time 10, so it has to wait. So the total waiting time corresponding to this is, the last waiting time is 10 in that particular case, minus the millisecond that is already executed. So 1 millisecond it is already executed, so it is 1 millisecond which is already executed here, and the arrival time, so arrival time is 0 at this particular case, so it is going to be 10 minus 1 minus 0 for process P1. Now look at process P2. So process P2, the total waiting time is 1 over here. Before that it is not executed anymore, so the execution time is 0 here, and it takes the uh, now it has the arrival time. So arrival time, here you can see that arrival time of the process P2 is 1, so it is 1 minus 0 minus 1. So ultimately process 2 has 0 waiting time, because it has to arrive at 1 and CPU is allocated immediately, so there is no waiting time for CPU, that process P2. Okay, now look at the process 3. Process 3 has a waiting time 17 over here. The previous execution is 0 and its actual arrival time is 2. Okay, so its actual arrival time is 2, that means it is not waiting from 0 to 2 moment. Okay, so once CPU is allocated, that difference has to be taken into account. Okay, so that will be the effective waiting time only. So this is the process 3, that uh, CPU is allocated at 17, not executed the previous segment, and then the actual arrival time is 2, so its total waiting time is 15 actually. Okay, similarly for process P4. Okay, once you computed this particular time, sum it, divide by the total number of process, will get the total milliseconds or the total quantum per unit process for waiting. Okay, so that is the task that you have to do. Okay, so this is the shortest remaining time, which is giving me the better result than the shortest job first. Okay, now look at another one, the priority scheduling. Priority scheduling says that if we have a number of process, what we can do, we can associate an integer value from 0 to increasing value. Okay, and in that particular case 0 will be the highest priority, or we can say the 1 will be the highest priority depending upon your starting point. Okay, the smallest integer must have the highest priority. Okay, and the increasing order of that particular number, that integer is having the least priority. Okay, now another task is, it could be preemptive, it could be non-preemptive. Okay, so whenever we are maintaining the priority scheduling, we can have the preemptive case as well as non-preemptive case. Okay, so SJF is the priority scheduling, where priority is inverse of the predicted CPU burst time. Okay, so there what we are doing, we are saying that whenever we have the least CPU burst time, that has to be executed first. So that is inverted concept of the priority scheduling. Okay, so if the highest CPU burst time, that has to be allocated in the last. Okay, so the priority scheduling has the two issues, that it may cause the starvation situation. That means if any particular process has the least priority, then it is possible that CPU is not allocated to that particular process. The least prioritized process is never allocated the CPU for execution. Okay, that is called the starvation. Okay, so what we can do, we can change its priority. The starved process priority can be changed with respect to time. Okay, so what we can do, we can use a small value so that we can change the priority of that starved process. We can increase the priority by a small quanta uh, on a specific time. Okay, so after, let's say, t1, this is updated. After t2, it is further updated. After t3, it is further updated. By this way, we can improve the efficiency, we can improve the priority of that particular process, and there will be a certain moment then CPU get allocated to that particular star process, and it will get executed. So that concept is called as aging. Okay, so with respect to time, we can increase the priority of that starved process so that CPU get allocated to that uh, starved process. Okay, so priority scheduling may have this particular uh, concept. Now we'll look at the round robin scheduling. That round robin scheduling says that each and every process may have a definite quanta for the execution. Okay, rather than looking at the priority of the particular process, rather than looking at the CPU burst time of the particular process, okay, rather than looking at the arrival time of any particular process, what we can do, we can say that this is the particular resource which is equally distributed among all. Okay, so CPU is allocated to each and every process in a round robin concept. Okay, that means for a particular specific time. So if I say that, let's say, delta is a time quanta. Okay, and each and every process has a CPU burst multiple of delta, then delta time is allocated for the CPU for any particular process to get executed. Okay, so it is possible that within that particular delta quanta, process is executed completely, or a partial execution is done, and further it has to enter into the ready queue for its next turn. Okay, so we allocate the CPU quanta to each and every process one by one in a repeated cyclic manner. Okay, so we'll look at the example of this particular question. uh, so again, it will uses the FIFO, first in first out. Okay, so it uses the ordinary queue, but the switching is done with the help of this particular selected time quanta. Okay, so we'll look at the example of these two process one by one. Okay, so we'll start with the gate previous year questions here. Just look at this particular question. Try to solve this because it is shortest remaining time first question. So we have already discussed. Just solve this particular process and let me know the corresponding outcome. Okay. So this is the process P1, P2, and P3. Okay. Process P1, P2, P3, and P4 has certain arrival time and the CPU burst time. Just try to solve this particular question and let me know the average waiting time. It is asking about the average waiting time in millisecond. Okay, just look at the question. Just solve and give me your solution in the chat box. Meanwhile, I am solving here and just compare your solution. Okay, so P0 appears at 0th moment. So P0 is allocated, P1 is allocated at 0th moment. At 1, there is no process appeared, but at 2, process 2 is appearing. Okay, for that particular time quanta, 2 CPU burst has been uh, utilized by this particular process. So the remaining time is 10 over here. But P2, in case of P2, the remaining time is 4 only, okay, which is lesser than 10. So this will get allocated. So P2 get allocated at this particular moment. And at moment 3, at the time unit 3, another process appears. So its time is going to be 3 now, remaining time. And there is 3 processes, process P1, P2, P3. And look at the remaining time. P2 has the remaining time 3 only, though that means P2 will continue. Okay, at moment 4 there is no process, 5 there is no process, 6 there is no process. So it will utilize the complete execution time. So 2 plus 4 is going to be 6. So this will continue to get executed at moment 6. Okay. So process 2 will get executed till 6. Now this process 2 is out of the race. It is terminated. Okay. Now uh, at 6 there is no other process, because uh, at arrival time 6 there is no new process. So there is only two process, that is process 3 and process 1, and out of which process 3 has the least remaining time. So process 3 is selected for the execution, and in that particular case it will get executed for 2 unit of time. Let's say process at arrival time 8, there is another process P4 that has the waiting time, that has the burst time, that is 5, and this is executed for 2 unit of time. So the remaining time is 4. So we have to compare 4, 5 and 10, out of which 4 is the least one. So it will completely execute. Okay, so it will take the entire time to get executed. So it will terminate at 12. Okay, now it is terminated because 6 plus 6 is going to be 12. So it is terminated completely. Now we have to compare the 5 and 10. Okay, so 5 is the least one, so that will get allocated. So P4 is allocated for 5 unit of time. So 17, 12 plus 5 is 17, and then P1 is allocated and the remaining time is 10 only, so it will terminate at 27. Now we have to compute the waiting time. So for P1 waiting time is going to be the waiting time, that is 0 minus the previous execution. So 0 minus previous execution is 0, minus the arrival time, and the arrival time is 0, so it is going to be 0. Waiting time for P1 is going to be 0. Waiting time for P2 is going to be P2 is 2 minus previous execution is 0, and the arrival time is 2, so waiting time corresponding to P2 is again 0. Waiting time for P3 is going to be 6 minus previous allocation is 0, minus arrival time is 3. So in that particular case it has to wait for 3 CPU bursts. And look at the P4, sorry, P1 is wrongly computed because its waiting time is 17 over here. Okay, 17, and it has executed for 2 unit of time. Okay, and there is arrival time is 0, so it is 15 rather than 0. Okay, now look at P4. P4's waiting time is 12 and previous execution is 0, and its arrival time is 8, so it is going to be 4 over here. So this is 15 plus 3 plus 4 upon 4, plus 0 is also for process 2. So it is going to be 15 plus 7, that is 22 by 4, that is 5.5. Option C should be the correct one. Yes, Kunal has the right answer. What about Mamta? What about Ambrose and others? If you are not able to reach to this particular solution, please let me know. What is your outcome? Okay, I'm waiting for your response. If you do not have any doubt, please let me know so that I can proceed further. Shall I proceed further? All right. Since there is no response, I'm just switching to the next question. Look at this particular question. So consider the following process with the arrival time and the length of the CPU burst given in millisecond. The scheduling algorithm uses the primitive shortest remaining time first. Again, the same question on based on the same algorithm. but we have the different parameters over here. So just run this, try to solve this particular question and have the solution. So we have four processes with the different arrival time with the different CPU burst. The same algorithm has to be applied. Just solve and give me the solution here. I'm also solving this particular question here along with you. Let us match the solution. All right, so it is asking about the turnaround time. It is not asking about the average waiting time. Okay, so how you have computed the turnaround time? So in that particular case, you have to actually look at the different formula. That turnaround time is basically having the relation between the this completion time and arrival time. Okay, so what we can say, the turnaround time is nothing but the completion time minus arrival time. Okay, so I was just computing the average waiting time here. Okay, so this is not required. So what you have to do, you have to simply calculate the uh, completion time minus arrival time. So completion time of the process 1 is 20 minus the arrival time is 0 plus the completion time of process 2 is 10 minus arrival time is 3 plus the completion time of process 3. The completion time of process 3 is 8 and the arrival time is 7 plus completion time of process 4 is 13 minus arrival time is 8. Okay, just find the sum of this, divide by 4 and you'll get the solution. uh, Give me the answer. So Kunal Dubey is saying that it is 8.25. Yes, Kunal has also the correct solution, that The burst time plus the waiting time is the turnaround time, that another mechanism that you can use for the computation of the uh, turnaround time. Okay, so we have an various approach of calculating this particular solution. Okay, so this is going to be, let me have the solution here, 20 plus 7 plus 1 plus this is going to be 5. So this is 28 plus 5, 33 by 4, 8.25. All right. So 8.25, option A is the correct one. 8.25 millisecond will be the time taken by turnaround time, average turnaround time of this particular process uh, for shortest remaining time first. All right. Very good, Kunal. Just solve this another question. So consider the following CPU process with the arrival time, and the length of the CPU burst is given in milliseconds in this particular case. So again, four process. I have the four arrival time, different arrival times, and the CPU burst. If it is preemptive shortest remaining time first scheduling algorithm, uh, to find the waiting time of all the processes. Okay. So since we have done the similar kind of question, I'm just uh, okay. So here you have to predict actually the uh, value. So this is fill in the blanks kind of question. Okay. So this is GATE 2017 question. Rather than having the option here, you have to fill the time, calculated time over here. Okay. Now in this particular case, you cannot wild guess. In the previous cases, there are A, B, C, D option. You can, if you are not able to solve that, you can actually fill by simply taking any particular question. But here you cannot have the wild guess. You have to solve this particular question. You must know the right procedure to solve a particular process. Okay. So I'm skipping this particular part. It is very easy. The same process that we have done in previous two questions that we have to do. Okay. So I'm just leaving this particular part. Jump to the next question. All right. Look at this question. Now we have the priority. So we have the process. We have five processes here, which has the corresponding arrival time, CPU burst time, and the priority. Okay. So consider the set of process with the arrival time, CPU burst time, and the priority. Now here it is point to be noted that zero is the highest priority. Okay. And sometimes it is possible that in question there is a twist that the largest value has the highest priority. Okay. Ideally, it is treated that the least value is highest priority, but it may be twisted in the question that highest value may be given the highest priority. Okay, so you have to be very careful when you are reading the particular question. This is shown below. None of the process has the IO bus time. Okay, the average waiting time in millisecond of all the process using the priority scheduling. Preemptive priority scheduling. That means if any particular process has the higher priority appears at any particular time burst, at any particular CPU time, then the running process has to be shifted into the waiting queue. Okay, so you have to just solve this particular question. Try to solve this question. This is GATE 2017 question. So since P1 has appeared, P1 has appeared at zero moment. Okay, so if I draw the timeline, you can also say it a Gantt chart. So at zero, P1 is allocated. Okay, and since it has the priority 2, it can get executed till a particular moment. Okay, until there is another process appeared for any particular time. So look at the arrival time. So next arrival time is 2. So process P4 can start executing because it has the higher priority than this currently running process. Okay, so at 2 unit time interval, in that particular case CPU burst will come out to be 9. Okay, so it get reduced at this particular moment. It is updated, that is 9. Okay, so at 2 it P4 has started the execution. Okay, now it cannot complete the entire process because at timestamp 5 there is another process appeared and that has the highest priority. So P4 is allocated for 3 unit of time because at 5 there is another process appeared that is called P2. Okay, so it is executed for 3 unit of time, so remaining time is going to be 7 in this particular case. Now P2 has the highest priority, 0. Okay. So doesn't matter what other process is appearing for any particular instance, it will get executed completely because it has the highest priority in this scenario. Okay. So it is going to be executed for complete time. So it is 28 plus 5 is going to be 33 in this particular scenario. So process P2 is completely executed. Now up to this particular time, all the process has been appeared. Okay, because 12 is also passed, 9 is also passed, so all these processes are already appeared. So only one process has completed its execution, and now looking at the priority, there is process P4 that has the highest priority. Now that has to be taken into consideration for the execution. So P4 will get allocated, and that will completely exhaust the time. So 7 remaining time is allocated to this, so it will get executed for this up to 40. Then next priority is P1, so P1 will get executed, and P1's remaining time is 9, so it will get executed till 49. And then the next process is P3, that will P3 will get allocated for 12 unit of time, and in that particular case it will get allocated for 51 because that is 51. All right, 49 plus 12. And then the last process that is called P5, that is the only process that is remaining, that will get executed for 16 unit of time, so it is going to be 67. Okay, so that will get terminated over. Now calculate the waiting time corresponding to average waiting time for the running process. So average waiting time for P1 waiting time is going to be 40 minus 2 minus the arrival time, that is 0. So it is going to be uh, P140 minus 2 unit is executed first. Okay, and this, so it is going to be 38. All right, for P2, this is for P1. For P2, just compute for P2. P2 is uh, waiting time is 5, previous execution is 0, arrival time is 5, so it has no waiting time. Okay, P2 has no waiting time, so it is 0. P3, P3 is appeared at 49, executed previously, no. The arrival time is 12, so it is going to be 37. All right. Now look at P4. P4 is going to be 33 minus 3 units already executed, and the arrival time for P4 is 2, so it is 33 minus 5 is going to be 28. All right. Look at P5. P5 appeared at 51. It has a so long waiting time. Previously executed, no. Arrival time is 9. So it has a long waiting time of 41 units. Sorry, 42 units. Okay. So just sum it and divide it by 5 because there are 5 number of process, 32. This is going to be 75. 75 plus this one divided by, let me use the calculator here, and this is going to be 29 millisecond. So this is going to be 145 by 5, so 29 millisecond, and we have the right answer here for the Kunal again. I'm not getting any other answer from other user or the same answer from the other user. Any other user who is currently in live and solving this particular problem, please use your pen. Solve the question along with me. See, these are the straightforward question that doesn't have any like tricks or tips. Okay, you have to solve this question to get the answer. There is no shortcut for this type of questions, and these are the questions that will definitely give you the marks. Okay, let me switch to another question. Okay, consider the set of five processes whose arrival time and the burst time is given in this. Okay, if the CPU scheduling policy is round robin, okay, so this is the round robin scheduling with time counter 2. Okay, so what you have to calculate? You have to calculate the total waiting, average waiting, and the turnaround time. Okay, so two parameters you have to calculate: average waiting and turnaround time for this round robin scheduling. Okay, that means we start with the process P1. Only two quanta is allocated for P1. Okay, then P2 is allocated for 2 unit quanta. Then P3 will allocated 2 unit quanta. Okay, so Kunal has a question: how can we solve the synchronization problem in which the critical section is given? I found them very hard to solve. No problem, Kunal. I'll jump to that particular section again. Okay, I'll come to the process synchronization. Okay, we'll look at the various ways, whether it is hardware way or software way, whether we are using Mutex lock or we are using the uh, binary semaphore or the integer semaphore to solve a particular problem. Okay, so we'll look at the questions on that particular sections also. And after this particular session you'll found very comfortable in that kind of questions to get solved. Okay, don't worry. Just we take this particular question from the CPU scheduling, and then we'll jump to the process synchronization. Just solve this question and let me have the solution. I'm taking a pause of 2 minutes. Considering you are able to solve this particular question, give me the solution. Okay, can you tell me whether I'm doing the right thing or not? Am I following the right procedure to solve this particular problem or not? I'm allocating each and every time to quanta to each and every process. Is this the correct way to solve this particular problem? No, Kunal. I just want to see here that I am not considered the arrival time. Just look at the scenario here that P3 is assigned for evaluation at timestamp 4, while P3 is appeared here at timestamp 2. Okay, so P3 can get allocated. Now P4, which is appeared at 3. Okay, and that is allocated. So one ready queue should be maintained. Yes, that is the important task, that the according to arrival of that, the waiting queue must be, the ready queue must be maintained. Okay, so this is not the right way, that in which particular process are arriving, and which particular process is preempted and is already there in the queue, that has to be maintained. Okay, so I'm just redoing this particular task. That has to be maintained. Yes, Vidhan has the right approach. 5 to 7 में P1 आना चाहिए, because that is already in queue, है ना? We have not taken here into consideration that. So if I restart this particular process, initially at 0 time stamp, P1 has appeared into the ready queue. Okay, so P1 is allocated for the execution for 2 unit of time. At that particular moment, ready queue is empty. Okay, now the next process, P2 appeared into the queue. Okay, now P2 is allocated for next particular process. Whenever P2 is executing, P1 is further entered into the queue. Okay, and while P2 is under execution, at that particular moment P3 appeared. Now P3 has to be into the rear position. Okay, because P1 is at the front position. All right, so this is the scenario that we have to uh, taken into account, that P1 is in the queue. Okay, and the P3 is under execution. All right, sorry, P3 is waiting for the queue for this particular process to be executed. Okay, so just complete this, follow that particular queue mechanism to maintenance of this particular queue, and then allocation of this particular process. Okay, so I'm just going to quickly solve this particular question. You have to take care of this particular maintenance of the particular queue, so that you can pick the right particular process for execution of the this. Okay, so rather than picking any random one, you cannot means round robin doesn't say that you have to make a cyclic representation of P1 to P5, then P1 to P5, and so on. Okay, you have to actually maintain this particular ready queue accordingly. Okay, so at this particular moment, P3 will get executed. Okay, and then P1 will get executed for 2 unit of time, and at that particular moment, P4 has to be appeared, so P4 will get allocated for execution of 2 unit of time, so that is going to be for 2 unit of time. All right, and meanwhile P5 has appeared, so P5 has to be taken for 9 to 11, so this is P5, and then P5, since P2 is still pending and that is to be kept in queue, so P2 has to be selected for 1 unit of time, so it will terminate this one. Okay, then since P1 is already allocated, so there is 1 unit of time remaining for this. After P2 there will be P1 for 1 unit of time, so it is 13, and there is only the last element P5 to be executed at 14. Okay, is this the right queue? It is the right sequence of execution using round robin. Are you getting the same? All right, so just compute the turnaround time. We have already computed the turnaround time. Okay, so turnaround time is going to be uh, the completion time minus the what? We have just solved the completion time minus the arrival time. Okay, so the completion time of process P1 is, you can say, 13. So 13 minus 0 for P1 plus process 2 completion time is 12, so it is going to be 12 minus arrival time is 1, plus for P3, P3 is 5, so 5 minus arrival time is 2, plus P4, so P4's termination time is 9, minus arrival time is 3, plus P5 termination is 14, minus arrival time is 4. Just sum it, divide by 5, and give me the solution. 13 plus 11 plus 3 plus 6 plus 10. 13 plus 11 plus 3 plus 6 plus 10 is going to be 43 by 5. So it is going to be 8.6 millisecond. Okay, so 8.6 average turnaround time. Okay, now if we have average turnaround time, what we can compute? We can compute the waiting time as turnaround time minus burst time. Okay, so we know the burst time for each and every process. So we have computed the turnaround time for each particular process. So turnaround time for process 1 is 13 here, so it is going to be 13 minus the burst time, that is 5 for the process 1, plus for process 2 it is going to be 11 minus burst time is 3. Okay, plus for process 3 it is going to be 3 minus the burst time is 1, plus for process 4 the turnaround time is 6, minus burst time is 2, and for process 5 it is 10 minus 3 divided by 5. That will give you the average waiting time, and this is going to be 8 plus 8 plus 2 plus 4 plus 7. Huh? Is it so? सेम आ रहा है आपका? Okay, so this is the mechanism that through which we can actually compute the round robin scheduling algorithm that will give you the answer. So we can compute the average turnaround time. So turnaround time is nothing but the completion time minus the arrival time, and we can compute the waiting time, that is simply nothing but the turnaround time minus burst time. Okay, or we can say the turnaround time is nothing but the waiting time plus burst time. Okay, so through that we can compute the turnaround time and waiting time for each and every process, and then after summing all the value divided by the total number of processes, we can have the average waiting time and turnaround time. Okay, so that is related to the CPU scheduling. Okay, again we have the same question. Okay, we have different CPU burst time, arrival time, and the process. Okay, this is preemptive shortest remaining time first, so we have already considered this. Now in this particular case we need to compute this z value. Okay, so this is the question which is asked in 2019. We have to compute this average z value. Okay, so how do we solve this kind of question? So the CPU burst time is not given to us. Just look at the question. Okay, and it says that if the average waiting time for the process is 1 millisecond, the average waiting time is given here 1 millisecond. We have the rule to compute the average waiting time for uh, allocating this particular process and solving this to get the solution. Okay, so we'll follow that particular process, and we'll have the formula. Average waiting time is already known to us. We'll simply compute this value of z. Okay, so that you can do easily. Now I'm just looking at the various questions. Okay, so you have to compare these two. Okay, so if the time quantum of the round robin is 4 millisecond, then the absolute value of the difference between the average turnaround time of SJF and round robin. Okay, So first you have to find the average turnaround time using shortest job first for this particular process, and then you have to apply the round robin scheduling with the 4 millisecond quanta. Okay, and then find the average turnaround time, and find the difference between the turnaround time of SGF and the round robin. And it says that you have to round off up to two decimal places, so you have to give the correct solution up to two decimal places over here. Okay, so this is again not the big deal. You have to simply apply the shortest job first algorithm, compute the turnaround time, and then you apply the round robin with the time quanta 4 millisecond, compute the turnaround time, get the difference of these two, and round off the solution up to two decimal places. Okay, so rather than truncating the decimal value, you have to compute the solution with the decimal places. So you can go up to three decimal places, solve it, after the subtraction turn round off this up to two decimal places. Okay, so this is the simple question so far related to the scheduling. Okay, all right. This is the theoretical question that consider the following statement about the process state transition of the system using preemptive scheduling. Okay. So it is giving me the scenario for the preemptive scheduling that the running process can move to the ready state. Uh, Ready process can move to the running state. The block process can move to a running state. A block process can move to a ready state. Okay. Now you have to find the combination which one is true. Okay, you have to find the combination corresponding to all these, which one is going to be the true. Okay, so since it is preemptive, okay, since it is preemptive, in that particular case, you have to identify all the situation that what are the preemptive scenarios. Okay, so if any particular process is already running, okay, and it is shifted into the ready state, that means uh, it is preemptive because any high priority process can appear at this particular moment and it will acquire the CPU. Okay, in that particular case, the previous running process has to be shifted into the ready state. Okay, so in this particular case, you have to simply look at the round that life cycle of the process. Okay, you have to just memorize the life cycle of the process. Okay, so this particular option is also true. One is appear to be true. Okay, which is not in case of Kunal, you have not given the first as a true attempt. If you look at the process life cycle, there I have told you that, just let me go back to that particular slide. Look at this. One process is already in running state and there is interrupt. In that particular case, the running process is preempted. Okay, preempted means in that particular scenario, the allocated CPU is deallocated and the high priority process has allocated the CPU. So running process has to be shifted into the ready queue. Okay, and this is preemptive situation. Okay, this is non-preemptive situation. This is non-preemptive situation when running process is terminated. This is non-preemptive situation when running process is shifted into the waiting state. So this is the non-preemptive situation. Okay, but this one is the primitive situation. Okay, so first one has to be the true. Okay, so the running process can move to the ready state. It is preemptive only when there is another process. Okay, now look at the second option. A ready process can move to the running state. Definitely, if high priority process is there, then the scheduler has to pick that particular process and dispatcher has to allocate that. So any process which is already running has to be deallocated. So that is the primitive scenario. A blocked process can move to the running state. A block process cannot directly move to the running state. It has to switch into the ready one. Okay, because scheduler has to pick any particular process from ready only. So option 3 is not the correct one. Okay, a block process can move to ready state. That is true. That is I'm saying. Okay, so option 1, 3 and 4 is going to be the true. That means C should be the correct option. Okay, in that particular case, C should be the correct option only. All right. Okay, so we'll start with the process synchronization. We'll quickly look at the concept of the process synchronization. That our objective is that we have n number of processes running into the system. Okay, they are trying to utilize the CPU. They are trying to utilize the resources. They are trying to access the different hardwares. And now operating system has a task that each and every process must work in synchronized manner so that the resources are properly utilized, CPU is properly utilized, there is no situation of starvation, there is no situation of deadlock. Okay, so that is the task of process synchronization. If n number of concurrently running process, so concurrently running process means all the processes are executing parallelly. Okay, and they may demand the shared resource, they have the certain shared resource among them. Okay, so utilization of that shared resource must be done properly. Okay, so uh, that is another task. Another issue is that each and every process must have its own normal section as well as the critical section. So the critical section is that particular section where the shared resource is to be written or read. Okay, any particular process is trying to read or write the shared resource in its program body, then that particular section, that small code segment is known as the critical section of the particular program. Okay, so it is the restriction that if any particular process is entered into its critical section, then no other process can enter into the critical section. That is the very important point, that if any particular process is executing its critical section, no other process has to enter into the critical section. It has to wait for the first process to execute its critical section. Now there is another criteria that it could be preemptive, it could be non-preemptive. Okay, so if it is preemptive, okay, if it is preemptive, in that particular case, uh, the previous process has to leave its critical section and another process has to be allocated for the critical section. Okay, so we'll look at this particular process by simple example, that uh, the consumer producer problem, that we have two buffers. Okay, producer has to produce the items and consumer has to consume the items. Okay, so the situation is like, if producer is producing one particular item and that is same time consumed by the consumer, so there is no problem at all. Okay, so there is a sync between the producer and consumer, that one is consistently producing and other is consistently uh, consuming that. Okay, so the counter which is incremented by the producer is properly decremented by the uh, consumer. Okay, but what if the producer is failed to produce the item? Okay, in that particular case, consumer is trying to access a particular empty buffer. Okay, that is one issue. Another issue is that if consumer is unable to consume the item properly in time, in that particular case producer is going to produce the item, and in that particular case one scenario may be that buffer is full and consumer is not consuming the items. Okay, now in that particular case producer has to wait. It has a deadlock scenario that producer has to wait until the buffer is empty. That producer cannot produce the beyond that particular limit, and consumer cannot consume the empty buffer. Okay, so that is the scenario that we have to maintain the consistency between the shared resources. Okay, so maintaining the data consistency is the basic task of the process synchronization, or it is the important task, you can say, between the cooperating process or concurrently executing process. Okay, so this is an important task of process synchronization, and this is the critical section that we have already discussed. That critical section is that particular section where the shared resources are trying to be accessed by the particular process. Okay, and each and every process must ask permission to enter into the critical section, that is called the entry section, and after completion of that entry section it has to exit, and after exit there must be a remainder section of the entire program. Okay, just look at this particular code fragment. So here you can see that there is a entry section of the particular critical section. This is the critical section of the program. Okay, once it is executed, it will exit the critical section and the remaining section has to be executed. when this particular process is executing its remaining section, another process can enter into its critical section. Okay, so in that particular case, there is no asynchronous behavior. Okay, so one process has completed its critical section, another process has to enter into its own critical section. But if two processes are parallelly trying to enter into the critical section, let's say there is one particular file and two processes are trying to write onto that particular file at the same time, then there will be data inconsistency, that one process has written something while meantime another process has overwritten that. Okay, so both will presume the different value. First will say that I have written alpha, while second will say that I have written beta. Okay, so both will presume different value and accordingly they will calculate further. So it will produce you the inconsistent outcome. Okay, so the consistency should be maintained by the operating system, and therefore this process synchronization is very important task. Okay, so just look at this particular example, that process pi. So it has a particular turn. Okay, so turn is allocated as j. If it is j, then process j can enter into the critical section only. Okay, so it will simply produce that if pi is executing a particular critical section, j has to wait. If pj has entered into the critical section, pi has to wait. Okay, so the progress says if no process is executing in its critical section, then there exists some process that wish to enter into the critical section. तो अगर जिस समय कोई प्रोसेस एग्जीक्यूट नहीं कर रहा है क्रिटिकल सेक्शन को, at that particular moment cpu can be allocated to any other particular process that can execute the critical section. Okay, that is called the progress. Okay, so it is important to ask that progress कंटिन्यूअस होना चाहिए, प्रोग्रेस वेट नहीं करना चाहिए, प्रोग्रेस एक लॉन्गर ड्यूरेशन के लिए होल्ड नहीं होनी चाहिए. सो इफ no other processes are entered into the critical section, at least any particular process must be selected by the cpu scheduler, so that it can further utilize the cpu to enter into the critical section. Okay, to execute the critical section. Okay, so that is called the progress of the execution. Okay, so that progress must be consistent and bounding waiting, that whenever any particular process is progressing, other process has to actually wait for the uh, allocation of the cpu so that it can enter into the critical section. And this waiting is basically looped waiting. Okay, looped waiting means it is waiting as well as checking for the status of uh, the exit of the critical section of any other process which is already allocated to cpu. Okay, so once it will get notification that any other process has been deallocated, it will enter into the critical section. So it is not only the waiting, it is not the infinite time waiting, it is waiting as well as checking. So it is a kind of loop which is waiting and checking. So it is called as bounded waiting, or it is spinning. Sometimes it is called as spinning. Okay, so it could be preemptive or non-preemptive, that we have already said. In non-preemptive situation, it is possible that there is a race condition. Okay, if there is a kernel mode execution, in that particular case, hardware is allocated to any particular process, and once the allocation process is allocated to any particular, once the resource is allocated to any particular process, another process can or that particular process can demand for the other resources. Okay, so this is called that when two computer programs processes are threads, so any process are thread attempting to access the same resource at the same time and cause the problem to the system, the race conditions are considered as a common issue for the multi-programming or multi-threading concept. Okay, so this is the scenario that at the same time two resources cannot acquire the same shared resource. Okay, so to avoid this particular race criteria in non-primitive situation is the required scenario. Okay, so this is one solution, that is the simple hardware solution which is given by the Peterson, that the two process solution, that we can have the simple flag. Okay, and once flag is set corresponding to any particular process, that process can only access the that particular process can enter into critical section, and another process has to wait. Okay, So it is the situation, or it is the solution only for two processes. Okay, so here if you see that here, the same process, that the previous process, flag is set corresponding to the ith process, and the turn is marked as j. So if just look at the condition, while flag j and turn is equal to j. So if the flag j is true and the turn is equal to j, in that particular case, in both the cases, if both are true, then only you can enter the critical section. Now look at this, flag I is set true, so flag j is false at this particular moment, and turn is j. So one condition is meeting, another is not. In that particular scenario, it has to wait. That means process I can enter into the critical section, but not the j. Okay. So just look at the scenario that mutual exclusion is preserved when pi enters into the critical section, if and only if flag j is marked as false. Okay. Or turn is simply marked as j. So both the situation has to be uh, maintained, so that only one process can enter into critical section, another has to wait. Okay, and that wait is nothing but the bounded waiting. Okay, and one process is consistently executing, that is maintaining the progress. So these three criteria has to be maintained. That mutual exclusion says that if any particular process is entered into critical section, rest of the process has to wait. Progress, that means at least one process is consistently executing its critical section. And bounding waiting, that means all other process has to keep watch and wait kind of scenario, so that it cannot enter into the infinite waiting concept. Okay, so these three conditions should be met. It is not the accurate solution, since it is very old concept. So some hardware synchronization mechanism is used. Okay, that is based on the locking. Okay, since uh, locking through hardware actually requires a lot of fabrication along with the processor. Okay, so since uh, hi Vanshika. Okay, so I'll come to discussion with you. Let me finish this topic. Okay, so synchronization with the hardware requires a lots of fabrication along with the hardware. Okay, so on the same flat bed of the CPU processor, you have to maintain different circuitry, so that you can acquire the lock with respect to the resources. And as number of resources are increasing, that number of locks are going to be increased. Okay, so this has some drawback. Okay, so the scenario says that when the operating system using this particular hardware synchronization mechanism, they are not broadly scalable. Okay, but because due to the changing scenario, we need to have an operating system which can actually have the scalability. Okay, it can adopt the coming scenario. Okay, you can run your program into 32-bit system, you can run your program into 64-bit system, you can run an application which is very older. Okay, so that scalability concept must be there. Okay, if number of processes are going to be increased, it can easily handle. If number of resources can be increased at runtime, it can handle. Okay, that kind of scalability and flexibility must be maintained. Okay, and if the hardware locks are already maintained for four resources, you cannot increase the fifth one. Okay, so that is the drawback with the synchronization with this particular hardware concept. Okay, so there comes another concept, that is mutex lock. Okay, so what it does, mutex lock says that we can have the two method. Okay, so this is the software solution. Okay, so this is the operating system designer build the software tools that solve the critical section problem. So mutex lock is the software solution that is simply provide a lock by simply having two functions. One is called the acquire function, that will acquire the lock, and release function, that will release the lock. So once a particular process has acquired a particular lock, okay, so it will enter into the critical section, rest other has to wait. Okay, and the waiting process has to check the condition of the release. Okay, and if the release is enabled in that particular case, another process can acquire the lock. Okay, and it should be atomic in nature. So atomicity says the non-interruptible means uh, no other high priority task can enter into the critical section forcibly. That means if any particular process has acquired the lock, whether it is uh, least priority process or high priority process, whatever, if any particular process has entered into the critical section, that is atomic in nature. No other process can actually forcibly uh, cause an interrupt to release that. Okay, so this spin lock has to be applied onto the process. Just look at this. This is the shared resource. If there is one process, it will acquire the lock. It will enter into this. The second process has to wait because this shared resource is already allocated to the process, and it is not only waiting; it is bounded waiting, BG waiting, that it is consistently checking as the release status of this particular acquired lock. Okay, so this is the concept of mutex. Okay, so mutex again is somewhat limited to the number of process. Okay, so what we have another mechanism that is called semaphore. Okay, so semaphore is the important aspect that you have to uh, check. So semaphores are nothing but simple variable, ordinary user variable, you can say. Okay, and they can vary by having the value. Okay, so what you can do, you can have a simple value that is called as binary value. So you can assign a semaphore as 0 and 1 value, or you can assign n number of value to, or you can say any integer value to a semaphore. Okay, or a variable which is defined as semaphore may have any value, any integer value. Okay, so there are two types. If we define by this, there are two types. One is called binary semaphore, another is called integer semaphore or counting semaphore. Okay, so the counting semaphore can have the integer value that range over the unrestricted domain. It can have any value from 0 to infinite. Okay, and the binary semaphore is simply having the two values that is ranging from 0 to 1. And let's say 0 is simply initialized as 0, semaphore initialized as 0. That means it is not acquired the lock. If it is 1, that means lock is acquired. Okay, so by this way we can actually uh, represent this particular binary semaphore. And if you thoroughly look at this particular scenario, 0 is unlocked and this is locked. Okay, so this is nothing but the mimicking mutex lock. Okay, so the binary semaphore is nothing but the mutex lock. So that is mean for the restriction on two process. But if we have n number of process and each and every process has, let's say, n number of instance of the resources, like our system may have connected with the 5 printers. Okay, having 4 hard disks, all right, 3 monitors. So this scenario is possible, and in that particular case we can have the hardware instances. Okay, that is called the hardware instances. If multiple instances are there, in that particular case we can apply the counting semaphore for solving such kind of synchronization problems. Okay, so just look at the scenario that how we can solve this particular problem. So if it is simple single instance of a particular problem, that could be easily solved. I'm just skipping this particular theoretical concept, just jumping into the direct solution, how you can solve a particular process. Okay, if any particular problem is given to you, how could you solve, and what will be the accurate solving mechanism. Okay, so look at the synchronization problem, that these are the classical synchronization problem, that bounded buffer, that is producer consumer problem, that we have seen, that we have a bounded buffer which is accessed by producer and consumer as well. Okay, so producer cannot produce more than the limit of that particular buffer. Consumer cannot consume uh, beyond this particular limit, that if buffer is empty, that in that particular case it cannot consume. Okay, and there will be a proper sync between the producer and consumer so that this buffer is properly utilized. The readers and writers problem, that let's say one particular file is shared among a number of processes. So uh, if all the processes are reading, then it is permitted. If uh, someone want to, any particular process want to write, then all other has to wait, so that it can maintain the consistency. Okay, dining philosopher problem is the another problem, that let's say 5 philosophers are there for the lunch or dinner. In that particular case, each and every philosopher has a one fork in between them. Okay, while having the lunch, they have to pick two forks at a time. Okay, while there is only one fork in between the two philosophers. So consider that there are five philosophers, then there are only six forks in between them. Okay, and each and everyone has to eat by using two forks at a time. Okay, so if one philosopher has picked two adjacent forks, then another philosopher has to wait because it doesn't have the adjacent fork right now. Okay, so we have to solve this particular problem by synchronizing, by devising a mechanism, by generating a rule so that they can share this particular shared resource, because fork is the shared resource at this particular moment. So they can use this particular fork in a particular rule so that each and every can execute its critical section, they can complete their dining scenario. Okay, now looking at the solution aspect, if we look at the algorithmic point of view, we may have the two approaches. If resources has only one instance, I'm asking about the semaphore case. If there are n instance, uh, resources may have one instance or an instance. Okay, if there is one instance only, in that particular case, what we can do, we can simply allocate the resource request allocation graph. We can have the resource allocation graph. In that particular case, we can easily determine whether there is a cycle formation or not. If there is cycle formation, then that will cause a deadlock scenario. Okay, by that way we can easily solve this particular problem. Otherwise, what we can do, we can check whether particular process has multiple instance of the resources, and in that particular case, resource allocation graph will not be the right mechanism to solve this problem. Okay, in that particular case, we need to apply the banker's algorithm to solve the problem. Sorry, we need to apply the semaphores, n semaphores to solve this particular problem. Okay, the counting semaphore. Okay, so the counting semaphore can be solved by this particular case. Just let me have the scenario here. Okay, just look at this particular question. Let me solve this particular question for you, and then you'll get the mechanism how it is being solved. Okay, the counting semaphore was initialized to 10. So the, let's say the semaphore value s is simply initialized as 10 here. Okay, then 6p weights operation and 4v signal operations are there. P or the wait operation is nothing but the request, and V or the signal operation is nothing but the release operation. Okay, so this is the scenario that 6P and 4V operations are running in this particular process. Okay, so what you have to do, operations are completed in this particular semaphore. The resulting value of the semaphore will be what? Okay, so you have to determine what will be the resulting semaphore value at this particular moment. Okay, are you getting the question or not? This is very old question, Kunal. Vidhan, Nisu, are you there? All right. So just let me give you some more detailed theoretical aspect over here. If I jump to this particular slide, are you able to see this slide? Process synchronization. Kunal, please confirm whether this slide is visible to you. Okay. So this we have already seen. Okay. So we are talking about the semaphores. So here just look at this, the bounded buffer problem and the reader digest problem that we have already seen. I'm just jumping to the direct solving the particular problem. Okay, so resume this particular process with this single resource allocation. If we have a single resource, we can use the resource allocation graph so that we can easily solve a process. And we have, okay, let me go back to the processor with this. Yes, this is the monitoring semaphore and all. Mhm. All right. So what it says that okay, we have two process P1 and P2 and S1 to happen before S2. Okay, so these are the two critical sections that has to be entered. Okay, so S1 must be happened before S2. In this particular case, P1 must be entered into the critical section. Okay, so P1 has to be initialized with the sync. Okay, and in that particular case it has to be entered into this. Once it has executed, it will signal for the sync. Okay, once it signal for the sync, P2 is waiting for the sync. Once it is notified, P2 will get allocated the signal. Okay, and accordingly it will execute the critical section of P2. All right. So it says that can we implement this by the counting semaphore? Yes, we can do that. We simply allocate the value and accordingly we'll solve this particular problem. Okay. So that is the concept that we have to apply the semaphore concept. Okay. So this semaphore can be of any type. I told you that it is a variable of any type. So it could be a list type, it could be an array type, it could be an structure type. So semaphore can be defined by any particular type, but it is ultimately holding an integer value. So here you can see that this is having the value. If it is linked list, the node must have the data value, and that value is nothing but the integer value. Okay, so by that way we can easily implement the this particular concept. Okay, so just look at the example here that we have already discussing. Okay, just look at this particular example, how we can solve this particular process. Try to solve it and let me know if you are able to solve this or not. So here you can see that the initial semaphore value is 10. Okay. So what we can do, we can perform 6 P operations. Na? 6 P operations means 6 instances of the same process can be allocated to uh, all the running process. Okay, so they can perform, they can enter into the critical section because they have the multiple instances. 6 process can enter into the critical section. All right, so what we can do, we can have the deallocation of the 6. So 10 minus 6 is simply performed. Okay, so the new semaphore value is going to be 4 at that particular moment after 6 P. Okay, so 4 will be the value at this semaphore. Okay, and when 4, so 6 processes have entered into the critical section. Okay, so only 4 semaphore value is currently available with us. All right, and when 4 has notified that they have executed their critical section, so they will send the notification, they will send the signal. So 4 has only notified us. Okay, just look at this particular scenario. When 6 has entered into this, because one particular uh, this semaphore, counting semaphore, says that this 10 or this particular numeric value is simply representing that we have this much instances of the shared resource. Okay, so we have 10 instances of the shared resource. In that particular case, 6 has been allocated for critical section execution. Okay, so right now we have only 4 semaphore value. That means 4 instances are left with us. So semaphore updated value is going to be 10 minus 6, that is 4. And once 4 has notified us, then the current semaphore value is going to be, so all free resources has to be added with the existing semaphore value. So it is going to be 8 and this particular moment, isn't it? Yes, Kunal has the right answer, that the semaphore value is, updated semaphore value is going to be 8 at this particular moment. Okay, so this is the only mechanism that when you have the, so you have to know like what is the value of this particular semaphore. Okay, and what is the meaning of this. So the meaning of this is that there are 10 instances of 10 instances of same shared resource. ठीक है, that means we have, let's say 10 printers are available with us. Okay, so my semaphore value is 10. Okay, so if 10 instances are available, 10 printers are available with us, 6 are trying to print, so I can easily allocate 6 printers to them. Okay, out of which 2 is still printing and 4 has notified that they have already printed, they have given me the signal. Okay, so 4 V signals have been received to me. Okay, that means right now I have only 8 printers available. 4 already, at the initial time 4 was empty, and 4 has deallocated that particular shared resource. So right now I have total 8 printers available with me. All right, so the semaphore value is going to be 8 at this particular moment. So answer corresponding to this is going to be 8. Okay, look at this particular question. Two processes P1 and P2 need to access the critical section of the code. Consider the following synchronization construct used by the process. Here, wants 1 and wants 2 are shared variables. Okay, wants 1 and wants 2 are the shared variable. तो दोनों ही required है, दोनों के लिए required है wants 1 and wants 2, which are initialized to false. Okay, initially they are initialized to false. Okay, so this is the initial value which is initialized to false. Okay, which one of the following statement is true about the above construct. So just look at this particular program and let me know which about this is correct. So this is the critical section entry. After the execution they will come out and execute the remaining section. Okay, so this is the remainder section of this P2. Okay, remainder section is separate deallocated here. This is the remainder section of the P2 over here. So P2 will enter into the critical section. After the completion of this critical section, it will exit out of this and execute the remaining section. So it says that it does not ensure the mutual exclusion. So look at the 3 properties of the same this process synchronization: mutual exclusion, bounded waiting, and progress. These 3 should be maintained. Okay, these 3 should be maintained. So just look at this. P1 enters into the critical section while true. So while true is infinite true. Now wants is converted into true. Wants 1 was already false. So wants 1 was true. While wants 2 is true. Okay, while wants true is true. But this is not true because initially that was false. Okay, while true was not true. Wants 1 is true and this is not true. And if it is not true, if it is false, in that particular case it will come out of the loop. Just look at the semicolon here. That means after the semicolon it will jump out of this particular semicolon. So it will enter into the critical section. It will convert the wants 1 into false and enter into the remaining section. All right, now look at the P2. While true, wants 2. Okay, wants 2 is simply converted into true. Initially it was false. While wants 1 is entered into true. Okay, while wants is true because that is false already, so it will come out of this particular loop. Okay, and enter into the critical section, and wants 2 is converted into false. Okay, Now we have to check these conditions. It does not ensure the mutual exclusion. It ensures the mutual exclusion, है ना. Wants वन ट्रू था तो ये false था, जब wants टू ट्रू था तो ये false था. Okay, so it includes the, it maintains the mutual exclusion. Okay, so that ensures the mutual exclusion. It does not ensures the bounded waiting. It does not ensures the bounded waiting. ऐसा भी नहीं है, bounded waiting है. While it is true, it is converted into true, and it is consistently in loop looking for the statement of wants one as a true. Okay, so this is the bounded waiting. So it is waiting for the, it is ensuring the bounded waiting. So statement true, this is not the true statement, B is not the true statement. Okay, A is also not the true statement because that ensures the options. It requires the process enter into the critical section in strict alteration. Okay, so strict alteration means एक बार ये enter करेगा फिर एक बार ये enter करेगा. We are not able to determine which one. Okay, तो P2 पहले enter कर सकता है, then P1 enter कर सकता है, या P1 enter कर सकता है, then P2 enter कर सकता है. Okay, and because after the termination, every time, let's say P1 terminated, okay, after P1 termination, again it will enter into the, let's say P1 again want to enter into the critical section, it is again permitted because it is independent of P2, है ना. ये वाला true नहीं होता है, in that particular case it will come out of the loop and it will enter into the critical section. So it is only dependent on this wants one. P1 is dependent on wants one, P2 is dependent on wants two. Okay, in that particular case there is no strict order of the execution of the critical section. Okay, so P1 can request multiple time, P2 can request multiple time, and there could be any random order between P1 and P2. Okay, so option C is also not correct. Okay, now look at the option D. It does not prevent deadlock. It does not prevent deadlock but ensures म्यूचुअल एक्सक्लूजन. अब डेडलॉक कैसे होगा, डेडलॉक कैसे होता, देखो जरा, ये वाला प्रोसेस है, वांट्स वन इज कन्वर्टेड इनटू ट्रू. ओके, लेट्स से इस पर्टिकुलर मोमेंट पे ये अभी ट्रू हुआ है, क्रिटिकल सेक्शन में एंटर नहीं हुआ है, तभी प्रोसेस टू आ गया. ठीक है, सपोज प्रोसेस टू हैज एंटर्ड इनटू एग्जीक्यूशन. ओके, सो it is converted, the value wants one is converted into true. Okay, now look at this particular situation. While true, wants 2 is converted into true, and it is trying to access wants 1 as true. Because wants 1 is converted into true, it will fetch the value wants 1 as true. Okay, तो ये वाला क्या हो गया, यहाँ पे ट्रू हो गया कंडीशन. अब अगर ये कंडीशन ट्रू हो गया तो ये क्या करेगा, वेट करेगा जब तक ये फॉल्स नहीं हो जाता. ठीक है, चलो ये अभी वेट कर रहा है जब तक फॉल्स नहीं हो जाता. मीनवाइल वर्ड्स टू भी ट्रू हो चुका है. चलो अभी ये वाला प्रोसेस जब तक, क्योंकि क्रिटिकल सेक्शन में जा नहीं सकता तो इट हैज टू वेट फॉर द बाउंडेड वेटिंग. अब ये वाला वापस आएगा प्रोसेस में सपोज, तो उस पर्टिकुलर मोमेंट पे वांट्स टू भी ट्रू हो चुका है, तो ये भी यहाँ पे इनफाइनाइट लूप के अंदर आ जाएगा. ठीक है, वांट्स टू भी यहाँ पे ट्रू हो चुका है, तो ये भी वेट करेगा. बाउंडेड वेटिंग ये भी कर रहा है, बाउंडेड वेटिंग ये भी कर रहा है. दो ही प्रोसेस और दोनों बाउंडेड वेटिंग में है. दैट मीन्स इट इज क्रिएटिंग द डेडलॉक. ओके, तो म्यूचुअल एक्सक्लूजन तो इंश्योर कर रहे हैं, बट दे कैन नॉट प्रिवेंट द डेडलॉक. दैट इज द राइट ऑप्शन इन दिस पर्टिकुलर सिनेरियो. सो डी इज गोइंग टू बी द करेक्ट ऑप्शन फॉर दिस पर्टिकुलर केस. ओके कुणाल, all right, you have given the right answer in this particular case. Let me have the another question. Consider the question, consider the methods by process P1 and P2 for accessing their critical section whenever needed as given below. The initial value of the shared boolean value, so it is either true or false. So S1, S2 are going to be the binary semaphore. Okay, they are going to be the binary semaphore because the initial value of the shared boolean value is S1 and S2 are randomly assigned. Okay, so they are randomly assigned. In this particular case, which of the following statement describes the properties achieved? Okay, so before going to this, just look at the methods. Whenever you solve the process synchronization problem, with the semaphore, in that particular case, first you have to look at the methods. Okay, explore the methods, look at the three conditions, that is, it is following the mutual exclusion, it is having the process progress, okay, it is uh, having the bounded waiting or not. Okay, these are the three primitive conditions that you have to maintain. Okay, just look at this. Since S1 S2 are randomly assigned, we cannot say whether S1 is equal to S2 or not. Okay, it is possible that both are equal, it is possible that both are not equal, one may be true, one may be false. Okay, that both criteria you have to look. So the possibility is both are 0, both are 1, one is 0, another is 1, another is 1, this is 0. You have to look at all four possibilities. Okay, now look at this. If both are equal, then in that particular case, it will not, P1 will not enter into the critical section, but P2 will enter. Because S1 and S2 are equal, and here there is a not question mark, not, that means not equal. So it will come out of this particular loop and it will enter into the critical section. Okay, so when both are equal, in that particular case, whether it is 0 0 or 1 1, progress is there. Okay, progress is there. Mutual exclusion is also there, because P1 can only enter into the critical section or P2 can enter into the critical section. If they are not equal, if this particular situation is true, if we look at this particular possibility, if it is equal, then it will keep waiting while this scenario will be false, and if this scenario will false, P1 will enter into the critical section. Okay, so P1 or P2, one at a time, can enter into the critical section. So mutual exclusion is done. प्रोग्रेस की बात करें तो प्रोग्रेस भी हो रही है एट अ टाइम, एक पर्टिकुलर प्रोसेस इंटर कर रहा है क्रिटिकल सेक्शन के अंदर, है ना, तो प्रोसेस भी हो रही है. ओके, व्हाट अदर पॉसिबिलिटीज आर देयर? तो म्यूचुअल एक्सक्लूजन बट नॉट द प्रोग्रेस, तो ये तो ऑप्शन नहीं हो सकता. म्यूचुअल एक्सक्लूजन है, प्रोग्रेस भी दिख रहा है मुझे. प्रोग्रेस बट नॉट द म्यूचुअल एक्सक्लूजन, ये भी नहीं हो सकता. नीदर म्यूचुअल एक्सक्लूजन नॉट द प्रोग्रेस, ये भी ऑप्शन नहीं दिख रहा है मुझे. बोथ म्यूचुअल एक्सक्लूजन और प्रोग्रेस इज पॉसिबल, तो ये वाला ऑप्शन ज्यादा सूट कर रहा है. दैट मीन्स ऑप्शन 4 इज द करेक्ट ऑप्शन. इज दैट क्लियर टू यू? So you have to only analyze this particular methods. Okay, method used by P1, method used by P2. Every time in the previous question also we have to analyze the methods that is used by this. Okay, Kunal has a question that how progress is done if P1 में S1 is equal to S2 है, तो P2 को एग्जीक्यूट होने नहीं मिलेगा. कैसे नहीं मिलेगा भाई? If S1 is equal to S2 है, let's say both are equal, in this particular case ये वाला कंडीशन ट्रू हो जाएगा ना, P1 will be true. ठीक है, ये ट्रू है तो ये लूप से बाहर कैसे आएगा? इफ इट इज ट्रू इट विल इंटर इनटू द लूप, है ना. तो ये जब तक ट्रू रहेगा तब तक तो क्रिटिकल सेक्शन में जा ही नहीं सकता. और P1 अगर क्रिटिकल सेक्शन में नहीं जा रहा है, नाउ लुक एट दिस पर्टिकुलर सिचुएशन, ये भी 1 है, ये भी 1 है. ठीक है, तो 1 इज नॉट इक्वल टू 1, कंडीशन फॉल्स हो गया ना. अब कंडीशन फॉल्स हो गया तो ये लूप से बाहर आ जाएगा. लूप से बाहर आने का मतलब सेमी कॉलन तो यही है ना, क्रिटिकल सेक्शन लूप के अंदर नहीं है. जस्ट लुक एट द सेमी कॉलन. सेमी कॉलन वाइल के जस्ट बाद है, दैट मीन्स इसके जस्ट बाद वाइल लूप खत्म हो जाता है, तो ये P2 क्रिटिकल सेक्शन में एंटर कर जाएगा. ओके, और अपोजिट के लिए भी बिल्कुल ऐसा हो रहा है कि जब ये 0 है या 1 है या 1 या 0 है, उस कंडीशन में ये वाला सेक्शन ट्रू हो गया और ये सेक्शन ट्रू हो गया तो ये लूप में फंस जाएगा. ये वाला सेक्शन फॉल्स हो जाएगा बिकॉज बोथ आर डिफरेंट, तो ये लूप से बाहर आ जाएगा और लूप यहीं पे टर्मिनेट हो रहा है सेमीकोलन पे. सो इट विल जस्ट एंटर इनटू द क्रिटिकल सेक्शन. तो प्रोग्रेस भी है, म्यूचुअल एक्सक्लूजन भी है, बोथ आर ट्रू इन दिस पर्टिकुलर केस. ओके, ऑलराइट, look at this. 3 processes are there. Okay, so there are 3 processes, 3 binary semaphores are there. Semaphores are initialized to this one, Semaphores are initialized as S1 is equal to S0 is equal to 1, S1 is equal to 0, and S2 is equal to 0. Okay, so how many times the process P0 will print 0? How many times process P0 will print 0? Okay, just look at the methods first. I told you that analyze the method. Okay, so we'll look at the process P0. While true, because it can enter into the process, because that has been already granted, S0 is granted as 1, so that has the mutual lock. So in that particular case it will enter into the process execution. Okay, so uh, while true, wait S1, S1 is already 1, so it will enter into the critical section, it will print 0, and it will release S0 and S2, S1 and S2. Okay, that means when we have entered into process 0, uh, this will simply make, because S1 is, if you look at the scenario, S0 is 1, S1 is 0, and S2 is 0. Okay, so it has entered into the critical section and it will print 0, release S1, S2. That means S1 is converted into 1 and S2 is also converted into 1. Okay, now just look at another process, that process P1. When P1 has entered into the critical section, it will simply check wait S1. S1 is already 1, so it will release S0. That means it will simply convert S0 into 0. Okay, sorry, that will release S1. Sorry, it will convert S1. So S1 was already 1, it is converted into this one. Okay, and then let's say process 2 enters, so it is not going to basically print any particular value. Let's say process P2 said wait S2. S2 is already converted into 1, so it will also release S1. So S1 was already 1, so it is converted to 1, there is no change further. Okay, so this is going to be the final outcome corresponding to this. Let's say P0 again comes into the uh, execution. Okay, when it again comes into the execution, in that particular case it will look at the true, wait for S0. S0 is already 1, in that particular case it will again print 0. Okay, and then release S1, S2, which is already 1, so it is going to be 1 1, no change at this particular moment. So if you look at this particular scenario, that, sorry, if you look at this particular scenario, then if P1 P2 further do not want to enter into the execution, okay, if P1 P2 do not want to enter into the execution, in that particular case only two zeros are going to be printed. Okay, then if you look at another possibility that at least P1 is going to enter in in this particular process, then another 0 is also going to be printed. Okay, no, because we cannot bound P1 and P2 to be entered into how many times. So at least 2 is going to be printed in this particular scenario, that at least 2 is going to be printed. Apart from that, it is unknown to us that hey, how many times this particular process can enter into the execution. Okay, so they can enter into any number of time, any particular process can demand for any particular time entering into the critical section. Okay, so this is the task of operating system, to manage that how many times a particular process is entering into the critical section. Okay, isn't it causing the starvation to other process to enter into the critical section, and so on. Okay, for that particular task the semaphore or the lock criteria has included. Okay, so any particular process can demand for the semaphore and enter into the critical section. This is our restriction, that let's say P1 and P2 is only entered once. In that particular case it is exactly printing two times. Okay, and if it is entered in, any one is entered in process, another time, then it will increase the count. Okay, and once it is increasing the count, that means it can print up to infinite time. Okay, so if you look at this outcome, exactly once is not the correct answer. Okay, if you look at this particular scenario, exactly twice, exactly thrice, exactly twice is not the correct answer. At least twice, at least twice, and then more than two is possible there. So exact three is also not the correct answer in this particular case. Exact two is also, because more than two is possible there, then it is going to be at least two, at least twice here. All right. So this is another question related to the multi-threaded programming concept. Okay, so multi-threaded I have not yet considered. So this is another problem related to the uniprocessor system, which is time shared based. All right, and what you have to do, you have to consider the concurrent process p1, p2, p3, which has the shared variable d. So this is the semaphore. Okay, shared variable d is the semaphore initialized to 100. Okay, initially it is 100. So what you have to do, you have to find the minimum and maximum value corresponding to the y and x. Okay, you have to compute the x and y, and then you have to compute the y minus x. Okay, so this is that you have to compute the value corresponding to this. Okay, and the minimum and maximum corresponding value of x is simply represented by x and y. So x is nothing but the minimum d is nothing but the x, maximum d is nothing but the y. So you have to compute x minus y, so that sorry, y minus x, so that we can have the correct outcome over here. Okay, so if you simply see that d is initialized to 100, in that particular case, let's say p1 has entered into this critical section, then d value is going to be 100 plus 20. So it is calculated, computed this particular value, and then d is updated as new value, that is 120. Okay, let's say at this particular moment d has already read the value 100. At this particular moment, let's say p2 has entered into the critical section, then it is going to be 100 minus 50, and that is going to be 50. Okay, and if it is computed the value on updated value, then it is going to be 120 minus 50, and that is going to be 70. Okay, now look at this particular scenario. If d has read the value, initial value 100, then it is going to be 100 plus 10, then it is going to be 110. Okay, and if it is reading the updated value, let's say updated value is 120, then in that particular case 120 plus 10 is going to be 130. Is there any other possibility that we are computing the value of x and y, or we are computing the value of d, depending upon the different scenario, that the occurrence of or the entry of the critical section of p1, p2, p3 can be in any random order. Okay, that because all they are concurrent process, not the, all they are running parallelly. Okay, so p3 can get enter into the critical section, or p2 can get enter into the critical section, or p1 can enter into the critical section. Any particular order can be there. So p1, p2, p3, p2, p3, p1, or p1, p3, p2 can be any particular random order. Okay, looking at all the possibility, we just need to maintain the minimum and maximum value. Okay, so in this particular scenario, if we consider this, d is computed at, so just look at the addition and subtraction value, that this is subtracted by 50 and this is added by 20. So this can give me the maximum value, or addition after this followed by p3, or p3 followed by p1 will give me the maximum value. So 100 plus 10 plus 20 can give me the maximum value, that is 130, and the minimum value is, since 100 is the smallest value, the initial value, then 100 minus 50 could be the least value, that is 50 at this particular moment. So if I can calculate the value of maximum and minimum, then the corresponding value is going to be, how it could be 60. It should be 130 minus 50. Minimum is 50. Yes, it should be 80. Okay. So the right answer should be y is going to be 130, which is maximum among all the calculation. Okay. And minimum is going to be 50. That means x is going to be 50 in this particular scenario. So this is 130 minus 50, and that is 80. So 80 is the right outcome at this particular case. Okay. All right. So I'll take this particular question on process synchronization as a last question for this. Just look at the scenario. Consider the two functions increment and decrement shows below. Okay, so this is the increment function and this one is the decrement function. Okay, and both have the same shared resource s and x. Okay, so there are five threads, each invoking increment once, and three threads which invokes decrement once. Okay, so we have five threads, out of which uh, five threads each invoking once one increment. Okay, and three thread which is invoking one decrement. Okay, on the same shared variable x. So this variable x is five times increase and three times decrease. Okay, the initial value of x is 10. Okay, so initial value of x is 10. So suppose that there are two implementation of the semaphore, so it is possible that we can follow the binary semaphore or we can find the follow the counting semaphore. So two scenarios are given there, L1 as binary semaphore and L2 as counting semaphore. Okay, so what should be the outcome after these two execution? Okay, so it is showing that what would be the outcome after v1 followed by v2. Okay, after v1 followed by v2. Okay, so if it is binary semaphore, that means once it is acquired by one particular process, it will complete all the tasks. That means if it is allocated to a particular thread, it will consistently increment. So uh, because another process has to wait, binary semaphore means only one process can enter into the critical section, another has to wait. Okay, so let's say five times increment is already allocated. So one process has one thread has incremented, another thread is incremented, next thread is incremented. So five increment is first allocated in a sequence. So 10 plus 5 is going to be 15, and then three decrements are there, three threads are decrementing. So since all increment process has executed, then decrement has to be allocated into the critical section. Okay, so they can decrement one by one. So in this particular case, 15 minus 12 is 15 minus 3 is going to be 12. Okay, so the first outcome should be 12. So either option is C or D. Okay, then what we have to see, we have to look at the next part, that is the counting semaphore. Okay, in counting semaphore, initial value was 10. Okay, now it is possible that since there are 10 instances, x value is 10, so there are 10 instances at the right moment. Okay, so that means uh, sorry, this is initialized to 2. Okay, if it is initialized to 2, that means at a time two processes can be executed. Okay, at a time two processes can be entered into the critical section. Now look at the scenario that increment and decrement both entered into the critical section, increment and decrement both entered into the critical section. Okay, so what we are saying, that we are saying that increment and decrement both are entered into critical section first time. Second time again increment and decrement has entered into the critical section. Third time again increment and decrement has entered into critical section. And the next time, because three decrement has already done, then next time only increment and increment has to be done. All right, so just look at the value, what is going to be the value. Okay, so it has incremented the value, then the value is going to be 11. Okay, it has decremented the value, but at the same time the both cannot reflect. Okay, so this process has decremented the value, but it is still in execution stage. Okay, the final value of x at this particular moment is going to be 11. this particular process is still in uh, under process. Okay, then again in this particular situation, if you jump to the next critical section execution, let's say increment has evaluated. So increment is evaluated on this particular value 11. Decrement is also done, but it is still in under process. Okay, so two decrement is still in under process. Let's say again I'm okay, again I have incremented the value, let's say. So that is the scenario solution that is given to you. Let's say it is also incremented new next time, and this is still under execution. Okay, then this particular value is going to be 13. Okay, and after that particular 13, what will be the value corresponding to this decrement? 1 1 1 and so on. Okay, now this is the scenario that whether which particular task is performing first. Okay, which particular task is performing first. So the combination could be this one. Also the combination could be decrement followed by increment, all three decrement first and then followed by increment. But depending upon this particular semaphore value, we have to first allocate two processes at the time. Okay, so two increment process cannot enter because two write operation of the same time, same task cannot be done at the same particular moment. Okay, so what it does, it will simply uh, perform one particular operation and then will wait for the another one. Okay, just look at the scenario. Both increment and decrement will read the value of x as 10. Okay, one has done the increment operation while another operation is still in execution state. Look at this one. Now it is reading the value as 11. Okay, so increment has done while decrement is still under execution. Decrement 1 is still under execution operation. Look at the third increment. Okay, during the third increment, let's say the final value has been written. Okay, let's say the final value has been written. So 12 is subtracted three times and the final value is now at 9. Okay, at this particular moment, x will read 9. It will cause another operation, that is increment, because two processes can enter at the same time because semaphore value is 2. So another increment or decrement is done, another increment or decrement is done. So in this particular moment, you can see that decrement is done two times. So the value is going to be 7 here. 9 minus 8 minus 7. Okay. So this is going to be final outcome, that 12 and 7 is the possible option. 8 cannot be the option. Okay, because of, so here we have performed 3 increment and 5 increment and 2 decrement operations. So 3 decrement operations, sorry. Okay, so based on this counting semaphore, two processes can enter into the critical section simultaneously, but at a time only one can modify the value. Okay, that is the scenario, that at a time only one can enter into the critical section. Allocation is done to two processes, but only one has uh, the effect on that particular function. Okay, that affect the value of x at a time. All right. So now there is another important topic that is called deadlock. Okay, so deadlock is like whenever we are talking about the n number of running concurrent processes, they are looking for the resources and the shared resources. In that particular case, it is possible that one particular process holds the n number of resources and waiting for any other resource. Okay, so that may be the scenario that will cause the hold and wait deadlock. If some particular process has already hold some resources and not preempting that, that will also cause the deadlock. That means the particular required resource is not going to be allocated to any particular process. Another possibility is that process is holding some resources and waiting for another resource, and by this way it is causing a cycle. Okay, so circular wait is another possibility, that the processes are holding and waiting for a number of resources. Okay, and the mutual exclusion, that means only one process at a time can use the particular resource, so other process has to wait. And if the allocated process is not relieving that particular resource, then all have to wait for the infinite time. So that these are the four possible criterias. That means mutual exclusion, hold and wait, no preemption, and circular wait may cause the uh, deadlock scenario. Okay, so these are the four deadlock characterizations on which we can define the deadlock can arise based on these four criteria. Okay, so what we can do, we can actually break the deadlock if we are able to uh, hold a particular process to enter into any of these four condition. Okay, if we break the rule so that it can neither be the mutual exclusion, not hold and wait, nor preemption, means it can easily preempt the resources, or it is not involved in circular wait, then we can say that our process is not in deadlock scenario, or process is in safe state. Okay, so if there are one particular instance, then we can usually use the resource allocation graph, and there we can easily here you can see that pi is allocated with the rj, requesting for rj, and here you can see that rj is allocated to pi. That means pi is holding rj instance. Okay, j instance of the r resource. Okay, so just look at this particular graph, that P1 is holding R2 and waiting for R1, while R1 is allocated to P2. R2, one instance of R2 is allocated to P2, and P2 is waiting for one instance of R3. And one instance of R3 is allocated to P3. So this is not the deadlock scenario, because if we execute P3 first, then this resource is free. P2 can easily executed, and once P2 is executed, this will be free, and R1 is also free, and in that particular case, P1 will also get executed. Okay, so this is not causing the deadlock scenario. But if we change the scenario, like P3 is also waiting for R2, so it is involved in forming the cycle. Here you can see that it is forming the cycle, or this one is forming the cycle. Okay, so if there is a cycle that is hold and wait scenario and formed in cycle, then it is simply causing the deadlock scenario. Okay, uh, and look at this, the graph with cycle but not in deadlock. It is only permitted that if any particular process that can get executed and free the resource, and that free resource can be utilized by circular waiting process. So despite of having the cycle, we can say the possibility of deadlock is not there. Okay, so there are two basic facts regarding the deadlock, that if our graph doesn't have any cycle, then there is no deadlock, or if does have a cycle, then it is possibility that it can involve in deadlock, or it can not be a deadlock, depending upon the scenario, that resources can be utilized in furthermore. Okay, so these are the two possibilities, that these are the basic facts corresponding to the deadlock that should be handled. Okay, now how to solve a particular deadlock scenario. So the basic primitive observation is that we should not uh, happen this particular deadlock scenario. Okay, we should prevent, we should avoid to occurrence of the deadlock. Okay, so that any particular process cannot enter into the deadlock state. Okay, so the mechanisms are deadlock prevention and deadlock avoidance. Okay, so we can allow our process to enter into execution or the resource allocation only when that is the safe state. Or what we can do, we can allow our system to enter into the deadlock, and then we can determine which particular process is in deadlock, and then we'll apply the recovery mechanism over there. So three processes are there: one is deadlock prevention, deadlock avoidance, and deadlock uh, detection and recovery. Okay, so three mechanisms can be done to solve the deadlock problems. Okay, so we're handling the deadlock. So deadlock prevention says that out of these four criteria, that mutual exclusion, no preemption, circular wait, hold and wait, if we are able to block any particular one point out of these four, our process is done. That means process can be easily executed without occurring the deadlock. Okay, but if it is not possible for us to avoid this particular scenario, then what we can do, we can use the deadlock avoidance mechanism. Okay, deadlock avoidance mechanism, that we need to determine the safe state, and once we have identified the process is safe state, we can allocate the resources. Otherwise, we can uh, restrain all the allocated resources from that particular device and allocate it to another process to get executed. Okay, for that particular thing, we need to have the banker algorithm. Okay, so this is the resource allocation graph in avoidance. If it is single instance of the resources, and if it is multiple instance, in that particular case, we need to avoid, we need to use the banker's algorithm for this. Okay, so this is another important topic. Most of the questions from deadlock are asked by this particular topic, that is banker's algorithm. So you have to uh, be very specific about this particular concept. Okay, so must learn the banker's algorithm, must learn the data structure concept that are used in this particular. So matrices or linear arrays are used for this particular banker's algorithm for maintaining the available resources, maximum resources, allocation of the resources, and the further requirement, that is need of the resources. Okay, so we need to compute these matrices, and accordingly we can determine that what should be the order of the specific execution of the process, so that we cannot enter into the deadlock. Okay, we can just allocation of the resources to a particular process to check whether that is safe state or not. Once it is safe state, it will get executed, it will free the resource, all the free resources are further added with the available list, and then we'll further solve the next particular process. Okay, so each and every time we allocate the particular resource to a particular process to check whether that is safe or not. If it is safe state, it will get executed, and then we'll reutilize the resources. Okay, so maximum questions are based on the banker's algorithms in deadlock scenario. Okay, so you just go through this. I'll stop over here. We'll check if it is possible that we can have uh, any other another session on this particular uh, remaining part. Okay. Memory management is another important topic that you have to learn about. The cache memory management, page replacement algorithms. Okay, demand paging in virtual memory, and then like in main memory concept, the management of holes, the fragmentation, segmentation, and paging concept that we have to learn about. Okay, so these are the important topics that we have to take care for the GATE exam perspective. Uh, we'll see if we have another session on this particular topic further anymore. Okay, so I'll close this session over here. You can write to me, or you can write through the chat box. I'll try to answer your questions further. Okay, all right, thank you for today.